Hey, maybe we get started. Can you see the full screen?
I have
Okay.
trouble seeing the full screen.
You do? Oh,
Let's see, how can I? Sorry. Oh, here we go.
Let me try again.
Okay, now I got it.
Okay.
good.
Good morning. Okay, let's get started. We have a very tight schedule for this morning. Welcome everyone to the 2023 CESM Paleoclimate Working Group meeting. On behalf of the co-chairs, Samantha Stevenson, Ran Feng, and myself, Jiang Zhu, I want to thank everyone for joining this meeting. And I also want to thank the members of the NCAR Paleo group, Betty, Esther, and Sophia for helping organizing the meeting. So on the left, you can see our code of conduct for this meeting. So during this meeting, please offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, consider new ideas. The format of the meeting, as you can see, we have 5 discussion sessions listed here, and each session is 1 hour long and features 2 invited talks, each 15 minutes in total. And at the end, we have a general discussion for around 20 minutes. For the invited speakers, please leave 2 to 3 minutes for question. And I believe the session lead who help us chair the sessions will give you a 2-minute warning at your 13th minute if you haven't finished at that time. We decided to include those topics in the discussion session, partly because based on our understanding of the community interest. Fortunately, this has been confirmed by the results from the questionnaire in the registration form. So here, looking at the pie chart, we see that there were 42 people responding that they are interested in the high and variable resolution modeling. 38 people interested in better organizing, sharing resources. Another 32 in water isotopes, and 24 in a fast version of the next release of a community Earth system model, 23 interested in vegetation modeling, and another 20 in biogeochemical cycling. So today we will cover 5 of the 6 topics. And in the future, we will have opportunities to cover emerging new topics, such as fast CESM, as well as ice sheet modeling and ice sheet climate coupling. So the purposes of the discussion sessions are to showcase a few studies on new CESM capabilities, new science, get your insights on Paleoclimate Working Group science and development priorities, and to build connections and collaboration among the working group members. So to that end, we really encourage you to engage during the meeting, engage with us, engage with the speakers, and with each other. So if you have questions, comments to the speakers, you could either raise your hand in Zoom or put them in the chat box. And during the discussion part of the session, you could either raise your hand or use the Jamboard. We will put the link in the chat later. And for the Jamboard, by default, your input will be anonymous, but you could choose to add your name if you prefer. And we decided to include Jamboard here to really make sure every voice is heard, and we really value your input. So please engage during the meeting and enjoy the talk and the discussion. So I will stop here and pass over to our session lead, Betty, on the first session, variable and high resolution modeling. Betty?
So thank you, Jean. Yeah, will chair this session. I'm really excited about this new opportunity for paleoclimate that might be of interest to those of you that are trying to understand past climate. So we have two talks, one by Ping Chang and one by Sophia Makarich. And why don't you share your screens, Ping, and get started? I'll give you your 2-minute warning.
All right. Can you, oops. Oh, geez. Oh, sorry.
Can you put it, yeah, that's okay. Can you put it in full screen?
Yeah, that's what I'm trying to do.
Oh, okay.
Here we go. Can you see it?
Yep, great, thank you.
All right, so thank you very much for inviting me to speak about the high resolution CESM simulations. And some of you may already know that in the past 3 or 4 years, we have been working on a large number of high resolution CESM simulations. And this project involved many colleagues, and here are some of the names. I may have missed out some of them. So if you see your name is not on the list, I apologize. So what I'd like to do today is to give you a brief update, what we have done so far, and hopefully some of the results might be useful for what you want to do in paleo community, modeling community. So first, let me just introduce you this high resolution model configuration. So we're using a version of the CESM. In fact, it's actually an older version. It's the version 1.3. It's not the latest CESM version. And the reason we did that was mainly because of the computational efficiency. And so the model consists of CAM 5.3, and the dynamical core is a spectrum element, dynamical core, and which actually has much better parameterization capability than the FV dicore. And the length model is CLM 4, and ocean is POP, and then ice model. And we did backport the coupler, the new coupler, to this version of the CESM1. So the model resolution is that the atmosphere and ocean is running, the atmosphere and the land is running at a 1/4 degree resolution, and the ocean is running at 1/10 of a degree globally. And we turn off all the ocean parameterization, so there's no mesoscale, sub-mesoscale, and overflow parameterization in this run. And then we did a similar identical sets of a low resolution simulation using the same SC dicore, so that we can actually compare the runs apple to apple. And we ported the code to other machines, and so that we can actually use more computing resources to complete those simulations. In particular, I'd like to mention is the tech computer called Frontera. And we have made effort. In fact, Jim Edwards helped us to port the code over there and optimize the code. In fact, the code is running really well on Frontera. And without IOs, we can actually do 10 years in a day on 800 CPU nodes. And with high frequency IOs, we can do 6 years in a day. So that's basically the performance we get on that computer. It's very efficient for us. And the cost ratio between the high res and the low res is about 100. So meaning that running 1 year high res equivalent to 100 years low res simulation. So here are some of the simulation we have completed so far. So we completed a set of simulation to the high resolution MIP set, and those data sets has been published already, which is part of the CMIP project. And you should be able to get this data from the ESGF nodes. And then the second major group experiment we have completed so far is the standard CMIP DAC simulation. So we made a pre-industrial control simulation for about 650 years. And then we branch out and did a historical and future climate simulation under RCP 8.5 from 1850 all the way to 2100. And then we've branched out from that and then made 2 ensemble members of 1920 to 2100 climate simulation under RCP 8.5. And then we did some single runs under other scenarios and RCP 2.6, 4.5, and 6.0. And we also completed the 2 climate sensitivity runs, 1% CO2 transient climate sensitivity and quadruple CO2 equilibrium climate sensitivity simulation. Each of them is 150 years long. And then in addition, we did a 3 ensemble member of the AMIP simulation. So you can see there's quite a bit of simulation already being completed. And the final set is it's even a larger data simulation set. Is the decadal prediction ensemble. So we actually did a quite large set of 10-member decadal prediction runs, and starting from 1970 all the way to 2022. And 5 years long each prediction runs, and so we're currently working on a publication on this set of simulation. So the total simulation years we have done so far is about 4,000 years. So that's equivalent to 400,000 standard resolution simulation CESM, and we generate a very large data sets and more than 3 petabytes. And some of the monthly mean data sets already being released, and you can see this link here. So what I'd like to do next is just show you some of the highlights of the difference between high-res and the low-res simulations. And first, we took a look at the global climate sensitivity between the high-res and the low-res, taking a look at the transient 1% CO2 simulations. It turns out that the high resolution and low resolution has very similar climate sensitivity. So the increase in the horizontal resolution did not seem to change the global climate sensitivity. The difference is about 10%. High resolution slightly has a stronger sensitivity. But on the other hand, if you look the regional climate sensitivity, then you see some surprising differences. And in particular, here is a map showing the difference between the high-res and the low-res temperature changes in this transient climate simulation. And you can see that the in a high-resolution model, the Arctic Ocean warms much faster, and the Southern Ocean warms slower, right? So which means that the Arctic amplification is actually significantly stronger in a high resolution model than a low resolution model. So indeed, if you take a look the historical and the future simulation and look the average temperature over the Arctic reference to the global mean, and you can see the increase of the temperature over the high resolution model is significantly faster in the low resolution model. So the thick black line is the high resolution model simulated Arctic warming, and the thin black line is the low resolution model simulated, right? So what is interesting, what we find is that if we decompose this the warming into a Pacific sector warming, which is indicated by this blue line here, and the Atlantic sector warming, then what we find is that in fact most of the rapid warming in the high resolution model coming from the Pacific sector. It's not coming from the Atlantic sector. In fact, Atlantic sector, the warming is even slower in the high resolution model. So the question why that's the case. So we think one of the reasons the different warming we actually see in the Arctic region is through the Bering Strait. So here is the comparison of in the Bering Strait with the bathymetry in a high resolution model and a low resolution model. in the Bering Strait region, and you can see the high resolution model give you a much more detailed depiction of the bathymetry over the region compared to the low resolution. So if you draw a section along the Bering Strait, and Bering Strait is a very shallow channel, right? So you can see there's a huge difference, right? So in the low resolution model, in fact, there's only essentially 2 grid points through the Bering Strait. And in the high resolution model, of course, because the resolution is 10 times finer, so you can actually get a lot more detailed structure of the. This is showing the Bering Strait heat transport, and in the high resolution and the low resolution model. And if you look the time evolution of the simulated heat transport through the Bering Strait, and what we find is that the high resolution model is increasing much faster in responding to the CO2 increase than low resolution model. So this figure here, the red is showing the changes of the heat transport through the Bering Strait as function of the future CO2 increase. And the blue line is showing the low resolution model. The red is showing the high resolution model. And all the thin line here is showing the CMIP5 model, and the black showing the CMIP5 model ensemble mean. And you can see that the high resolution model is having a much larger increase in the Bering Strait heat transport. So that leads us to the hypothesis that the reason why we actually see a more rapid amplification in the Arctic region, perhaps is through the increased ocean heat transport through the Bering Strait, which actually triggers a faster, a stronger albedo feedback, and which enhance the regional melt, and then so leads to a Pacific-driven Arctic amplification. Wait a minute, I'm stuck here. Come on. Sorry, I don't know what's going on. Can you hear me?
Yeah, we can hear you.
Yeah.
My my screen seemed to be. Oh, here we go.
Oh, okay.
I don't know what's going on. I'm sorry for the mess up.
That's fine.
Do that. So the last thing I want to mention very quickly, I know I'm running short in time, is the eastern eastern boundary upwellings. I know the paleo community have some interest in study the upwelling in the past the climate, and one of the bottom message I try to send is that the high resolution model significantly improved the upwelling simulations. So here you can see in this column here showing the observed SST, OI SST along the California, Canaria, Peru, Chile, and Benguela region. And the middle panel here is showing the model, high resolution model simulated the SST along the coast. And you can see that the high resolution model give you a much more realistic simulation of the upwelling, a narrow upwelling region along the coast. And the low resolution model essentially misses all this detailed structure altogether. And one of the reasons for this much improved simulation along the coast, we believe, is really not only the winds along the coast, but more importantly, the wind stress curl along the coast, which is fundamentally important for driving this upwelling system. And because the model is doing much better with the upwelling, given more realistic upwelling, so we did a test to try to see whether the backhand hypothesis is actually working in this high resolution model, right? So the backhand hypothesis meaning that
Ping, 2 minutes.
Okay, I'm almost done. So
Good.
the backhand hypothesis arguing that there's in responding to the future warming, the land actually warming faster than the ocean. So therefore, as a result, there's enhancement in the land-ocean pressure gradient. As a result, you're actually driving the stronger coastal winds. So you expect a stronger upwelling response in the future under global warming. So we examined that in a high resolution model. It turns out that that's not the case, and in fact, in many of the upwelling regions, particularly in the southern hemisphere, we actually see a warming rather than cooling of the coastal water. So that's suggesting that the upwelling was actually weakened rather than strengthened along the coast. But anyway, for those of you who are interested in this study, we just published a paper. Be very happy to give you the details if you really want to know more about this. So let me just to summarize. Oh, geez. Just to summarize, the international collaboration facilitated the breakthrough global climate simulation at the eddy ridge spatial scale, and so as a result of this international collaboration, we have created the multi-centennial pre-industrial simulation, completed DAX suite, and initialized the decadal prediction. All these data sets, I think, can offer an excellent opportunity for the community to assess the potential benefits of the high resolution climate model simulation. So I'm particularly interested in collaborating with the paleo community, and I'm really hoping that the simulation that we have done can provide some basis for you to design your experiment and to learn something new about our climate. So I'll stop here. Thank you.
So thanks, Ping. If it's okay with everyone, I think we'll defer the questions until, and we'll have questions for both speakers during the discussion point time. So I see lots of clapping. So I assume, can you stay for the discussion, Ping, and answer some questions? Sure. Okay. Excellent.
Absolutely.
Okay. So our second talk is by Sophia, and she's going to talk about another way to increase resolution, the variable resolution capabilities that are available in CESM. So I guess Ping, unshare your screen, and then Sophia, share yours.
Okay, here I go. Let's see. Okay. Can you see that? Is that the right screen? Is that presenter mode, or is that the proper screen? Okay, great. Okay. Okay, so hi, I'm Sophia Makarowicz. I'm a new project scientist in the Paleoclimate group at NCAR. And today I'll be talking about opportunities for using variable resolution, or VR, CESM in paleoclimate research. I created this talk with the help of Adam Harrington, who's also in the Climate and Global Dynamics lab at NCAR. So this is a really broad, potentially broad topic. And so here's the general outline of my talk today. I'm going to talk about currently supported VR grids with CESM, why we should use VR in paleoclimate, and in general, common challenges that have emerged from previous work with VR. And then the main sort of topic, which is the hierarchy of opportunities to use variable resolution in paleoclimate. So there has been a major increase in the accessibility, documentation, and out-of-the-box functionality with VR in CESM. So in CESM 2.2, you could run a modern case with all three of these variable resolution grids out of the box. The first one is the CONUS grid, which refines from 1 degree to 1/4 or 1/8 degree over the continental United States. There's the Arctic grid, which refines from 1 degree to 1/4 degree. And then there's the Arctic Greenland ice sheet grid, which refines from 1 to 1/8 degree over the ice sheet. The reason why these grids and these simulations are particularly useful is that they capture both global climate patterns and then also complex regional terrain at a relatively low cost compared to a uniform high resolution simulation. So on the left, I'm just showing you the increase in topography that can be resolved as you increase resolution from about 1 degree to 8th degree over the Western United States. It's been shown in previous work that capturing this increased level of detail results in significant increases in the accuracy of orographic precipitation and snowpack. But then also at the same time, while you can capture this increased detail in your region of interest, here on the right, I'm showing you, estimates of costs for these different CESM2 grids. So the number of columns in the atmosphere on the x-axis, and then the estimated core hours per simulated year on the y-axis. And then you can see the difference in cost between a uniform 1 degree and then a uniform 1/4 degree simulation. And you can see these 3 VR grids that I just introduced to you are falling much closer to that 1 degree cost. They're still expensive runs, but you can see the savings if your question permits you to just look at one region of interest. But before I get into how we could potentially use VR for paleoclimate studies, I think it's important to know some common challenges that have emerged from previous work with VR. So the first one is inadequate scale awareness. So this is essentially means that you can get spurious circulation features that arise simply from your refined region of interest. So in this particular plot I'm showing here, it's an aquaplanet simulation where there is anomalous diabatic heating in this region that's refined in the black circular region. This anomalous diabatic heating leads to anomalous vertical motion and updrafts in the region of interest. There is divergence aloft, which leads to convergence outside of the refined region. So this whole circulation feature is forming just as a function of that refined zone and not an actual physical feature that's supposed to be in the simulation. So this is an issue that has sort of persisted in a lot of VR simulations. And so the main thing you can do is avoid refining regions with a lot of diabatic forcing and vertical motion, such as the intertropical convergence zone. The second issue I want to bring up is if you are designing your own custom mesh, you can have a situation where the grid refinement is too abrupt. So this can also cause spurious circulation features. So here I'm showing you 2 examples of an Arctic grid, one with the typical sort of scale of refinement from the 1 degree to 8th degree, where you can see buffer zones in between each level of refinement, whereas this grid on the right is showing you very extreme refinement from 1 degree to 8th degree over a short spatial scale. If you were to put these 2 different grids over the equatorial region again, which is what we see in the right-hand side, you can see these sort of tracks forming in the grid that is aggressively refined. These are tropical cyclones that are forming in that aquaplanet simulation simply because of that grid refinement, and they don't exist. They shouldn't exist in the grid where there is the proper amount of refinement. So this is all just to say that there's a general rule that you should have a 4-element buffer zone per halving of grid resolution. So that is sort of featured in that low refinement grid. The last issue I want to bring to your attention is that there is a large sensitivity to the physics time step in high resolution simulations. So it's commonly known that vertical velocity scales with increasing grid resolution in atmosphere models. And Harrington and others in 2019 showed this with a simple moist bubble experiment where they ran multiple simulations with CAM at different horizontal resolutions from 1 degree down to 1/4 degree. And they also scaled this moist bubble within the simulation with the same factor as the resolution. So smaller bubble, finer resolution. The gray lines here show you sort of the theoretical vertical velocity that bubble should display. And then if in these simulations, you were to fix the physics time step at 1800, which is the accepted physics time step for the 1 degree simulation, you can see that the vertical velocities of that bubble are significantly dampened. So they're much lower, particularly at high resolution. Whereas in this paper, they suggest a scaled approach to your physics time step where you use a smaller physics time step at higher resolution. And that allows you to reduce the time truncation errors that are causing that dampening of vertical velocity. So if you decrease that physics time step at high resolution, you can reduce these time truncation errors. So there are recommended physics time steps to use at these resolutions. Okay, now that I've gone over those 3 common challenges in VR simulations, I want to get to sort of the levels of ways we can use variable resolution in paleoclimate. So the first level is almost out of the box, do-it-yourself variable resolution, where we can take advantage of the out-of-box functionality of VR grids. So these are those same 3 grids that I showed you earlier, and the name of those grids. You could create your new case in CESM, run 1 line of code, and set up a modern day simulation with these grids. Now, let's say it could be useful for your paleoclimate interval of interest to just modify some climate forcings, such as greenhouse gas levels in your simulation. That would be very easy to do if you wanted to use CESM 2.2. So that's sort of the simplest case that I could imagine of someone using VR for paleoclimate. If you're interested in this, luckily now there is, a lot of documentation on how to do this. So on this page here, you can essentially look at all the component sets of CESM that are supported with these 3 grids. The second level is still do-it-yourself variable resolution, but it requires a bit more work. And so this is a scenario where those 3 different grids don't capture your region of interest and you want to create your own custom mesh. And so that is also very doable with the VR toolkit. And so this page here, this wiki page, provides a step-by-step guide from start to finish of how to create your own custom mesh on the modern topography, of course, with CESM2. So another sort of simple modification to this workflow I see for paleoclimate is, let's say you want to refine over South America, and you could learn something about your paleoclimate interval by modifying the elevation of the Andes mountain range. So you're sort of just modifying the modern topography with your custom mesh. That's another relatively simple way to use VR for paleoclimate. This next level is where the out-of-box functionality sort of goes away, and you'll need a bit more assistance to use VR for paleoclimate. But this new configuration is quite exciting. Adam Harrington just developed this simulation of coupling VR cam to fully coupled CESM2 with POP and SISM. So essentially in this, without getting too far into the details of this simulation, he is comparing just the effect of increasing the atmosphere resolution over the Arctic and comparing that with a uniform 1 degree atmosphere model. And he sees some very interesting changes that occur in the ocean. So a colder ocean temperature, as well as a stronger AMOC signal that arises from this adjustment to the grid resolution in the atmosphere. If you want to learn, if you're interested in this configuration or want to learn more about that work, I suggest you watch Adam Harrington's talk in the Atmosphere Working Group. It should be posted on YouTube. And then just, I'm just overlaying his this Arctic configuration coupled to POP on that same plot I was showing you earlier. So you can see you need about 10,000 more core hours per simulated year to include the POP coupled to the Arctic grid. And now this is sort of the final level, which I'm really excited about, which we're calling the quote unquote Wild West of VR CESM. And so this is where this is sort of active development. But the first component I want to draw your attention to is a configuration of VR CESM with water isotope tracers. So this is VR ICESM 1.3. And so right now, I don't have any major results to share, but I'm running a historical transient simulation from 1980 to 2005 with the CONUS grid and with water isotope tracers. And that is, I'm excited about it, but also my ultimate hope with this configuration is not just to run a modern case to compare with observations, but also to apply this configuration for paleoclimate. And then this isn't the best comparison between different simulations, but I wanted to give you a sense of different isotope-enabled simulations with CESM 1.3 and how much they cost. So I'm comparing a fully coupled uniform 1 degree simulation in the bottom left with the high resolution 1/4 degree atmosphere and 0.1 degree ocean, and then where this sort of CODA simulation falls between the two. These are expensive simulations. It costs about 80,000 core hours per simulated year for the CONUS simulation that I'm developing, but you could save a lot relative to a fully coupled isotope-enabled uniform high-resolution simulation if it suits your question. And then the last sort of piece that I think people will probably be very interested in is, if the modern topography, the modern continental configuration doesn't suit your interest for your paleoclimate interval, you want to create your own custom VR grid with paleogeography. Or
2
you
minutes,
don't want to.
Sophia.
Okay,
2
I'm
minutes.
almost done.
Good.
Or you don't want to use CESM 2.2. You want to use a different version of CESM with your variable resolution grid. So I guess this is also on level 4, right? So unfortunately, I don't have a workflow to give you of how to do this right now, but I'm very interested in sort of creating a parallel set of instructions in this alongside the sort of documentation that already exists for creating a custom mesh. What this will look like is essentially you have 2 options for creating a custom grid. You either provide a high resolution set of topography at 30-second resolution, or you can provide a 1/4 degree topographic file, and that is what is used to smooth to match your custom mesh that you create with this program. So I could envision a future where different paleoclimate intervals could develop their own high resolution topography files to be used for different custom VR meshes. So let me know if you're interested in that, and I can, start working on that more. And so just in conclusion, I hope that my talk has communicated that there's been major advancements in the accessibility, documentation, and out-of-the-box functionality of VR CESM in recent years. Using VR CESM in paleoclimate research is currently limited, but I hope I've communicated that there's lots of opportunity to apply it. So if you're interested in any of those levels I've described, feel free to reach out to me at my email. And I'll take any questions.
So thanks, Sophia. So before we get to questions in the discussion, we have about 15 minutes now. Can you, and maybe Jean can share back the screen for the meeting. So we just wanted to make you, as we go into the discussion, Ping mentioned interest in paleoclimate, and we're very excited that with the new supercomputer derecho, which is now on the floor in Wyoming, when we get access, we're going to be allowed, as part of these 2-month accelerated scientific discovery projects, to run what I call paleo weather. So it's basically using the same configuration as Ping mentioned for the IHES project, but then doing 3 time periods in the past. You all know mainly about these: the early Eocene climatic optimum, which has very high CO2, mid-Pliocene warm period, which is about what we are now. These are all equilibrium climates, and an LGM simulation with a very cold climate with low CO2. due to the hard work of Jean and Jesse, the IHES version now includes isotopes. So this will be run with isotopes and we'll are rerunning already the pre-industrial with isotopes as we wait for the machine to come available. So a key point of this is for either the high resolution or the variable resolution, especially if you're running the variable resolution with fixed SSTs, is you need to start out from some spun up ocean. Takes a long time. Can you go to the next slide, Jean? To run some of these, to get the oceans spun up. And so we just wanted to highlight here that there are a number of time periods where we already have available low resolution ICSM1 that would be interesting for the community to think about whether this fits within your research to either run the high res or the variable resolution, starting from one of these low res. And we'll also have in session 4 a talk by Keith Lindsay talking about spinning up the ocean, which will be very advantageous for paleo. So let's just move on and not spend too much time on this, and maybe just put up the questions. But first we'll ask for questions, and you can either put them in the chat, raise your hand in Zoom, or put them on the Jamboard. But just these are more general questions. What questions might people have for Ping or Sophia? And if I miss a hand, let me know, Jean. Well, you can think about them. I mean, it really is. Why don't you just put up, here we have Xunyun has a question.
Well, it's really exciting to see all the development. I have a question to Ping. So you mentioned that like this high resolution model uses spectral element dicore. Could you please explain what's the you mentioned that it's advantageous than the finite volume. So could you please explain what kind of advantage that you've seen? And the second question is, if you are using this scheme, how tracers are transported?
You'll have to unmute yourself, Ping.
So I'm not sure I'm the right person to ask the second question of yours, but in terms of the first question, the reason, my understanding is the reason the spectrum element, the dicore is preferred is basically for the computational efficiency and the fact that it's a much more parallelizable. So we can take advantage of a large number of nodes on the high performance computer system. And we're using on Fonterra, we're using 800 nodes, right? So you really need to be able to use a large number of computer nodes in order to get the through flow you want. So that's the main reason. I think that's my understanding. I'm not sure I can answer the second question. Maybe someone at NCAR can help answer that.
Hi, Ping, this is Adam. Okay. So you're just using CAMSE. You're not using CAMSE C-SLAM, which is has a separate tracer advection scheme than CAMSE. So I mean, is the tracer advection in CAMFV preferable to CAMSE? I couldn't say one way or the other, but well, actually, we've done some experiments with the isotope model. I think trying to advect deuterium excess around, and we did find that we had to use CAMSE C-SLAM to remove some what looked like spurious numerical errors in the tracer advection scheme. So I think that if Paleo wanted to use isotopes in this IHES branch, they should use CAMSE C-SLAM. And there's no reason it shouldn't be able to run. And I mean, it should be supported in that configuration to the best of my recollection.
Great, thank you for your answer.
I think Jean would say, but let's not take the time for that, that even SEC SLAM has some issues with isotopes over topography and that. So we should discuss this more. But Clay, question.
Oh yeah, nice talks. This is kind of just a general question. I was curious if in testing or in simulations where you're getting up to higher CO2s, if you've had any stability issues, because I know for paleoclimate, when we try to force in these really different climate states, one of the things we run into is stability in different model components. And so with either the IHESP or the variable resolution, has that creeped up with like the RCP 8.5 or the 4x CO2 cases and things like that?
As far as I know, we have not experienced any a major problem with the high CO2 simulation. The model seems to be behaving quite stable as far as we can. We run 3 ensemble already, so we have not seen any really weird behavior. And one of the interesting difference between the high res and low res, which I did not get a chance to mention. I mean, we have an overview paper if you want to. If anyone of you are interested in 2020, and one of the really interesting thing is the polynya in the Southern Ocean, and the high resolution model gets this multi-decadal polynya things, and the low resolution model does not have, and so that's very interesting feature. I'm not sure whether that has any, implications for paleo studies.
Thanks.
So Jean, can you or Sophia read the question in the chat? For some reason, my Zoom is not working the way it should, but I'll fix it here quickly, I hope.
I see a question from Eric that is, what is the spin up time for a customized VR grid? Do you mean the model spin up time of spinning up the atmosphere model with the VR grid, or spin up as in preparing a customized VR grid and seeing if it works in your simulation, like human work?
No, I'm just thinking of, if you probably are interested in coupled processes, you might even be looking at a Greenland ice sheet or something like that, a dynamic ice sheet. So, it would be nice if everyone could have their own customized grid, and these could be tailored to the specific sort of research interests of the individual. But on the other hand, if it takes, 50 or 100 years of spin up time to get to an equilibrium where things are sort of stable, because you're, looking at air sea fluxes and because of things to do with the land surface, then there could be some need to consolidate and have a smaller set of customized grids that are sort of more coordinated between sort of people with different interests. So where do we really stand on that?
So I think probably Adam could speak to this question more thoroughly than I could, but my sense from your question is, so once you have a spun up ocean, which is your 1 degree ocean, and then you decide to use this custom VR grid, you're essentially just spinning up the atmosphere model. That's in a configuration where it's just maybe atmosphere land coupling there. I'm not sure about coupling it with POP or SISM, but in that case, you're spinning up the atmosphere model. And so I've seen simulations where they run a year with their custom VR grid once they know it's working properly, and then the rest of the simulation is what they look at. That's in that specific configuration.
Okay, that's encouraging. Thanks.
So I'll read the other, and maybe it's not so much a question, and then we'll let Ren ask a question. Leslie asked about other VR grids that she thought might be of interest. For example, one over the North Pacific, where you have the Bering Strait, Gulf of Alaska, and thinking about paleohydrology of North American West. And I think this is, something as a community, and maybe groups of people getting together that have a common interest. I know the Western US is already quite a bit of interest that we did start developing and sharing these grids. And so working as a community, I think that's a very good idea. So Ren, you had a question?
Yeah, it's more of a clarification question to Sophia. Sophia mentioned that in one of the slide, if you have a strong diabatic forcing and vertical motion, if you refine over that region, you would have spurious vertical motions. I was wondering, but the well, we're very interested in looking at refining like the grid to topographic complex regions. For example, for the eocene time for the Western North America. But does that problem get solved if you enlarge your refinement region and create more buffer, like what you showed in the other slide, or it's just generally the high topography might be really challenging?
I don't think, Adam and I, which feel free to follow up on this, Adam. Mostly this is what I'm familiar with is sort of ITCZ, equatorial regions over the ocean. And in terms of simulating mountain regions, this issue doesn't come up as much, or if at all. So this is mostly over the ocean. Do you want to add anything to that, Adam?
Yeah, it's what you said is right.
Okay. Yeah, great. Good to know.
Okay, if there are no more questions, and there's some things in the chat you can read about spinning up also from Adam. Yeah, I think these questions we kind of know the answers to on the first two, and people have suggested other variable grids. I think Ping showed very nicely the advantages of kind of a higher ocean resolution, whether it's going through straits, Bering Strait, but I can think of other straits like the Gibraltar or maybe the Indonesian through flow or the Nares Strait, where that might be of interest, and upwelling zones. We know models have had trouble simulating the what the data says in terms of past climates in this upwelling zones, and it could have a strong influence on the continental regions. And then Sophia showed, that you can even go to higher resolution if you have a specific region that you're really interested in. We're talking about 1/4 degree in the global high res versus maybe 1/8 degree over the US. So depending on the science question of your research group or even a bigger community, I'm hoping we can all work together on that. The last point I put up there, because I realized even though this is a high res and a variable resolution session, there's still a lot of need by the community for lower resolutions. And I think Jean mentioned the fast CSM3. You want to run longer simulations. And so we really need all three still in our toolkit to be able to understand past climates. So I'll leave it at that because Jean gave us 5 minutes to take a quick break before we start the next session, which I know is going to be of a lot of interest on isotope modeling. And Ren's going to lead that one. So go get your cup of coffee or stretch your legs, whatever you need to, or just stay on and continue the chat.
Thank you.
And oh yes, thanks, Ping. That was great to have you. I didn't introduce where you're from, but Texas A&M.
Thank you.
Thank you. Thank you.
Thank
Bye-bye.
you.
Bye.
Bye.
I was wondering, Jane, if you have a minute, should we
Mhm.
try your slides and Jesse as well?
You mean share?
Yeah.
Okay, so Give me a second.
Great, I can see the full screen.
Okay.
Okay, Jesse, would you like to try?
Give me a second so that I can stop sharing.
Sure, hold on. Oh, whoops, wait. I had to share my screen first. That
Great, looks good.
worked. Awesome, cool, thanks.
Okay, so Jesse will go first, and then Jun will go second. It's the same at 13 minutes. I'm gonna give you a heads up.
Sounds good.
All right. Hopefully most people are back. Welcome back, everybody. So this is the isotope modeling section for the Paleoclimate Working Group meeting. We have two talks. The first one's given by Jesse Nussbaumer, who's a software engineer at NCAR, who has been really instrumental in developing generations of isotope-enabled isotope tracking-enabled functionality in CAM. Jesse, will you please share your screen and we can get started?
Great, thanks, Ryan. Okay, that still look good? Awesome, great, thanks. So yeah, hi, my name is Jesse. I'm a software engineer in AMP, which is the atmosphere modeling group under CGD and NCAR. I'm going to talk about kind of going what have we done to go beyond ICSM1, and then what still needs to be done, and what are the big challenges. So it's going to be a little different. That's going to be discussing somewhat kind of software issues, not just straight science, but I hopefully have some science results that people will find interesting as well. So yeah, let's just jump right in. So so this is ICSM 1.2, which is technically our currently officially released version of an isotope-enabled model. As you saw from the previous high resolution group, we're moving to this ICSM 1.3, which allows mostly to use like high resolution, the SC dicore and things like that. But for now, this is the current official one. And so this is like our cartoon graphic of what's in the model. And so, ICAM 5, ICS4, IPOP, that should be IPOP 1, whoops. River trainer model and CLM4. Right now, however, CGD is working on 2 versions ahead. So we already have CSM2 and they're working on CSM3. So CSM3 will have several changes, basically everything. So for some versions, like for CAM, we're just updating to CAM 7. So we're 2 versions of CAM, but we're still the same model functionally. CICE, the CICE model is 2 versions ahead, it's still the same model. Then there's the land model is updated to, they changed the name to CTSM, but it's functionally still CLM from a science standpoint. However, CLM went through, which we'll discuss, went through a pretty significant refactorization. And so it's in some ways, from a hydrologic standpoint, not the same model as CLM4. And then for the ocean, river runoff, and for what I don't have here, which is glaciers, we have entirely new models, right? So now CSM3 will be using MOM, not POP. We'll be using Mozart, or another one called Mizu root for rivers, and then CISM is the ice sheet model. And so none of those 3 have isotopes in them at all. So if we did want to try to move all the way to CSM3, we'd need to implement adding isotopes into all of these models. So why would you want to do this in the first place? Because what's wrong with CSM 1.2? So here's kind of a list. So one of the things is it lacks, CSM 1.2 lacks kind of general model features that a lot of scientists want to use, right? It doesn't have as complete biogeochemistry, which is what MARBLE is. That's for ocean biogeochemistry. It doesn't have dynamic vegetation like FATES, which I believe will be discussed later this workshop. It lacks nudging, excuse me, it lacks nudging to observe winds in the atmosphere. So a lot of times people want to do that when they're comparing against observations. So it's kind of missing general functionality, including what we just, variable resolution. It lacks that feature as well. That causes the next thing, it's lacking. You can use the SC dicore CSM 1.2, but it has problems. So it's generally lacking the functionality of that. Also, CSM3 will be adding even more dicores, including ones that the one that's kind of most popular right now is something called MPAS. It's lacking new. This is kind of one of those things that we never talk about, but always comes up, is that if using an old version of the model, a lot of times it lacks certain forcing files. There are certain, if you want to do emission scenarios or sometimes even paleoclimate forcings, it's missing those files, and you have to make them yourself. So it's just kind of a general burden, even if it's not necessarily a showstopper. Obviously, we improve models to try to improve models, and so it's generally, likely going to have larger biases or errors relative to newer models. And then right now, there's currently no plan to port CSM 1.2 to derecho, which is the new machine. Hopefully, though, ICSM 1.3 will just kind of cover that. But if someone needs this model specifically and we need to run it on derecho, then we'll have to put some effort into importing it. Now, that being said, I have been working, myself and others, for quite a long time on stopping and going on an isotope version of CAM 6, which is a CSM2 version. And that does have significant improvements from at least a software standpoint. And one is an updated cloud microphysics. And the real key about that is it has prognostic precipitation, not diagnostic. That matters a lot for isotopes during rain re-evaporation, because with diagnostic precip, you basically have to, it's basically the residual after you subtract one large number from another large number. And so isotopes are not a fraction of that small number, which can lead to all sorts of numerical problems. The prognostic precipitation, that goes away. You always have the kind of mass at every level, and so you can just treat it as any normal tendency would be. We have updated, CAM6 has updated boundary layer turbulence, shallow convection, and cloud microphysics scheme, moved away from the UW schemes to club. That is science improvements, but it also brings some challenges, which I'll discuss later. We can use the SEC SLAM die-core configuration in the CAM6 version. And that it kind of came up with the advection scheme. I'll show why that matters in the next slide. Then finally, it has more accurate aerosol physics and atmospheric chemistry. And but one big caveat is that we don't, CAM6 has to be coupled to CLM5, and CLM5 is not isotope enabled currently. So that's the one major downside. So why do we care about SEC SLAM, the affected scheme? So here were some results we ran with CAM5 physics, with the SE die-core, and with SEC SLAM, while basically developing the IHAS isotope enabled version. And we found that when you don't have sort of isotope mass fixers, and you try to run with just SE at 1 degree, or any 30s of approximately 1 degree, you get the top left slide, which if you don't know nothing, if you don't know a whole lot about isotopes, I can tell you that -900 is just wrong. It's just blatantly wrong. It is not, there's nowhere on earth I know of that is -900 isotope delta O18 values. But when we keep everything the same, so we're using the C-SLAM advection scheme, we're using SE any 30PG3 grid, it goes away. That error just goes away. And so this is clearly, basically by changing the advection scheme, you remove this clearly numerical anomaly. And this is a big deal too, because this is for just O18. If you were to look at DXS or O17XS or whatever, the errors would be even more significant, which is what Adam was talking about earlier, although I'm not showing it here. This is also kind of a big deal. I do want to mention this is a big deal from the numeric standpoint because, so Peter Lauritsen's kind of our numerics guy along with Adam Harrington, or at least, die-core guy. And, a lot of times they actually struggle with showing kind of real life implications of the advective scheme. They show, they can show that, of course, numerically it's better, you get more accurate, but it's hard to show like, oh, it has a huge climate impact per se. But for isotopes, it really does, right? Like this is clearly, we resolved this by applying a bunch of mass fixers in the IHAS version, but mass fixers aren't ideal. And so, if you want to have the most accurate isotope simulation possible with the SE die-core, it's better to use C-SLAM is basically the result. And if you want to simulate DXS and particularly O17XS, we might have to. So how does, in general though, how does ICAM6 compare to ICAM5? And so this is plots from a paper by Rich Fiorella in 2021. And I want to point out too that this is also with the developmental version of CAM6 that has not been like tuned per se. So this is kind of we just changed the physics. How do the isotopes change? And so these plots are all essentially the same. It's observed versus with a model simulating and the dot, and this is for GNIP plus like some other extra stations. So it's all precipitation monthly values. And so this is for O18, this is for DXS. I hope you can see my mouse. And then this is for the annual average, just kind of like long-term average. And this is DJF minus JGA, so an approximation of the seasonal cycle. And so you can see the annual average we get. So black would be if you're perfect. Green line is CAM5, ICAM5, and then the dashed lines are ICAM6. It's nudge versus free running, although it doesn't appear that nudging makes a significant difference. So you can just treat them kind of the same. But you can see that for annual average, the kind of like long-term average bias, we look a little better. Maybe DX would look a little worse. Didn't seem to make much of a difference. But for seasonality, we are significantly better. As you can tell, particularly for DXS, ICAM5 almost didn't have a seasonal cycle of DXS, where at least ICAM6 has one. It's obviously not perfect. Clearly a lot of work to be done, but there's clearly an improvement with seasonality. And there's some more analysis in that paper, but essentially that's the takeaway, is that without any tuning and without an isotope-enabled land model, we don't change the long-term bias in ICAM6, but we do seem to improve the variability, at least slightly. Along with that, beyond just the physics changes, there were some bug fixes. I think I'm going to skip that though. The only key one is maybe in ICAM 5, we did find a bug in the deep convection scheme. We're applying a tendency to the wrong state variable. It doesn't seem to actually make a big difference, but it's still clearly physically incorrect. So we have that. We do. I want to emphasize we do, or at least we will have that fixed in the IHES version. Fixing in the CSM 1.2 version depends on if people really need it. So beyond just the physics, we've also been working on specifically targeting the isotope physics. And one thing that was worked on, again, we did this for ICAM 6 is, and this was done by Marina Deutsch back in 2019. And one of the things that ICAM 6 provides you is the model calculates the supersaturation. Supersaturated matter is during fractionation, right? So if I'm depositing vapor onto an ice crystal, there's a kinetic fractionation. So basically you change the dxs, and that's a function of the supersaturation. For almost all previous models, including ICAM 5, that supersaturation value was just a function of temperature with a tuning parameter. So up here, these two top plots, those dashed lines that are literally straight lines, that's what that parameterization is, just this linear function of temperature. The black, gray, really the blue line is what the actual model supersaturation is predicted from the cloud microphysics. And so clearly you can tell that they don't, you can, if you're lucky, you can draw a line through it, but generally that pattern is not just a linear line. It's clearly varies. And that makes sense from a physics standpoint, right? Because supersaturation depends on temperature and humidity. It's not just a function of temperature. So, what happens if we use this blue curve here, and this is just present day versus LGM, but essentially you can kind of see they're pretty similar. But what happens if we use this real kind of curve here instead of these just straight lines? And we found that, again, you can look at the paper, it didn't make a whole lot of impact for delta 18O or delta D, but it did make an impact for DXs, particularly over Antarctica. And so for a fact, for the LGM time period, it made it, approximately 8 per mil change in the the DXS over Antarctica, which is significant. It's like large enough to be seen from, in proxy records. So the other advantage of this too is, of course, we removed a tuning parameter. So now if there's a bias in the model for DXS, it's a bias in the actual model physics, not just in the way we tuned the model in the isotope sense. The other thing, I don't have a lot of great plots. This is the best one I'd say to find. So the other thing that ICAM 6 has is it has 17O and it has tritium. So I know tritium's not used a whole lot, but delta 17O is starting to become like the cool new isotope kit on the block. And so so this is just a plot of delta 17O. It looks from an eyeball test passes. We theoretically can do now 17O excess, and then even we added the physics in, do mass independent fractionation, but so far neither of those seem to work properly. And again, that might be a numeric standpoint. We never ran the SEC slam, so it might be worth doing that experiment to see if we can get a better 17O excess value. But for right now, 17O excess doesn't seem to work, but it should. So it's a bug. It's fun. The other thing, I might be running low on time. I've been timing this really well, but I'll go real quick. The other thing, we don't have an isotope enabled CLM5, but we do have the physical CLM5 model. And one of the things that buys you is the ability, when you're doing water tagging in the atmosphere, to be more specific about your land sources. And in particularly, you can split up the land moisture flux into its 3 components, which is basically ground evaporation or lake evaporation, transpiration from plants, and then intercepted water that's evaporating, so canopy caught water. So here's a paper from Tyler Harrington and Chris Skinner in Massachusetts. Obviously it's looking at the US, but those pie charts are basically showing what's the distribution of transpiration, canopy evaporation, ground evaporation from a tagging standpoint. So basically it's improvement. This isn't necessarily isotope specific, but it gives you a more accurate water tagging feature. So what are the big, so you may say, okay, well, great, we're doing great. Nothing's in our way, but we do have some major roadblocks to getting like a fully estimated CSM2 or CSM3. And the biggest one is the land model. So, you know, over this left plot, this is ICLM4. So this is the CLM4 version. You can see there's all sorts of hydrology or physics processes that are going on. And we don't have that in CLM5 or CTSM. For when we're using CAM6, we basically have to just do a bucket model. And we can make our bucket model a little fancy. We have 2 buckets, and one's a deep and shallow, and so they have different residence times and things. But at the end of the day, a bucket model is not going to capture the complexity of a full land model. And we know that land models do seem to have an impact on water isotope values. And so that's kind of a major roadblock. It basically will take a scientist or software engineer fully dedicated time to implement water isotopes in the new land model. The other roadblock is Club itself. I have a version of Club where the water isotopes are just shoved into there, but the problem is Club isn't owned by NCAR. It's owned by Vince Larson at University of Wisconsin, Milwaukee. And they have multiple different customers, including the Department of Energy and others. And so they probably wouldn't like us if I just shoved water isotopes into their code as well. So there needs to be a decision made of like, do we kind of have our own NCAR have our own isotope enabled version of Club that we manually keep up to date? Do we try to figure out an alternative kind of middle way solution that's less intrusive? Regardless of what the decision is, it would also take person time to get isotope enabled Club up to kind of the head version. Finally, the other thing which I didn't talk about in that graphic is going from CSM 1 and 2 to 3 is there's a change in the coupler. So both CSM 1 and 2 use MCT and something called coupler 7 to couple all the component models together. And so we have to have hooks in. Zhang and I and Esther others have worked on building those hooks in. But with CSM 3, we've switched over to something called NuWAPC and CMEPS. In theory, the hooks were passed over, but just odds are that they probably were broken at some point. And so again, this is kind of just pure software engineering, but it'll take someone to have to go in and make sure that all of the isotope fields are being passed properly through the coupler from one component to the other. Okay, so yeah, I just want to end with like possible discussion questions we could have, which I think are repeated from what they're going to show later. At the end of the day, if the community wants water isotopes and water tracers in CSM2 or CSM3, we need resources to do that. Basically, you know, we need someone to have the money and the time to do so. And so, you know, maybe we need to decide on if we should write a proposal. Should a proposal fund a grad student? Should it fund a postdoc, software engineer, whatever? But ultimately, you know, there's hundreds and hundreds. This is the land model side. It's been estimated hundreds and hundreds of person hours are needed to get a land model version enabled. And so it's kind of the major barrier. And then beyond, this is more of kind of a general question or philosophical.
Sorry for the disruption, Jesse. I think this will be great to talk about during the discussion.
Okay, then we can skip. All right, so I'm done. All right, thanks.
Yeah, our next speaker is Jun Lee, who is the assistant professor at Brown University, who has very accomplished career in studying climate physics, the climate ecology interactions, as well as developing isotope-enabled models. All right. Great, looks great.
Okay.
Oh, wait.
Well, thank you for having me here. Sorry. So I incorporated stable water isotopes into CAM2, which is an old model, and I didn't study isotopes for a long time, and now I'm coming back to the isotope study and has been working on adding isotopes into the GFDL model. So first, I'll introduce why I decided to add isotopes into the GFDL model. So this is the speleothems, and I think one of the most important findings from stable isotope proxy is how East Asian monsoon is related to the insolation. And what we see is that during the high insolation period, there's low isotope values, which implies a stronger monsoon, and the patterns are coherent among different cave sites in Asia. So there have been three major hypotheses explaining why we have this isotopic change. So the first speleothem data, what they were arguing is that it is actually representing the local precipitation change. The problem is that previous model results show that following the insolation, the precipitation change is relatively small over East Asia. And the second hypothesis is that even if precipitation change is small, we can have isotopic composition change if we have changes in the upstream region. So if precipitation increased in the, for example, Indian monsoon region, and then that water vapor is evicted to the East Asian monsoon region, that could make the isotopic composition low. And the difficulty is that, we see the divergent response of isotopes and precipitation, but often the change is too small to explain. So the change that we observe is about 3 to 5 per mil, which is about half of the whole tropical change. So this is actually a very, very large change. So for the whole tropics, what we see is somewhere between 0 to -8 per mil. But following the precessional cycle, we observe 3 to 5 per mil change. And then the third hypothesis is that changes in the seasonality is influencing the isotopic composition. So this is somewhat complex, but I'm going to go through this step by step. So the red box is the Asian monsoon region from 24 degrees north to 36 north, and then starting from April to September. And spring rainfall has high delta 18, and summer rainfall has low delta 18. And this is and the shades are precipitation. So this precipitation movement in the Asian monsoon region is related to the location of the jet. And often what we see is that, in the equatorial regions of strongest jet, where we have largest wind shear, if there's moisture supply, we see a large amount of precipitation. So as the jets move northwards through the summer, we see this precipitation belt moving toward the higher latitude. And what John Chang was arguing was that when we have stronger summer insolation, we have less spring rainfall, which has high delta 18, but more summer rainfall, which has low delta 18. Unfortunately, this hypothesis has not yet been proven. So what I've been very interested in was, which is the most reasonable hypothesis and why. So I mentioned that, I've worked with the older CAM. So this is the wind velocity U at 200 hectopascal in June. And the line is NCAR CAM 2. And the arrow shows where the jets are for the NSIP reanalysis. And what you see is that, at least for this older version of the model, the jets are further away compared with the reanalysis data. And as a result of this, there isn't a lot of rainfall in the Asian monsoon region. And then, change of insolation didn't bring rainfall over this region either. So I've been looking at different models, and I was looking at the GFDL AM2. Again, this is relatively like at this point old model, and what I saw was that at least the location of the jet is closer to the reanalysis data. So I ran the GFDL model with two different insolation. So one with the hot summer, cold winter in North America, and the other is milder summer, milder winter. So that's December perihelion. June perihelion is a stronger insolation in summer. And I had eccentricity of 0.05, so that's maximum eccentricity. What I thought was that if I don't see any difference with highest eccentricity, I probably don't have to study this further. So this is the result. And what you see is that there's a large increase in precipitation over the Indian monsoon region and also over the East Asian monsoon region. So precipitation change is really large. It's like, some local regions, it's more than 50% during the summer. And then I was looking at the results for the slab ocean model as well. So left is the fully coupled model, the one that I just showed, and the right one is with the slab ocean model. I mean, the results seem to be actually quite similar to the previous results that showed large precipitation change in the Indian monsoon region, but relatively small precipitation change in the East Asian monsoon region. So I tried to find why, at least in this GFDL model, they have different precipitation response. So for the slab ocean model, similar to John Chang's hypothesis, the jets move northwards and became weaker. But with the fully coupled model, the location of the jet is quite similar for both runs. And I looked at why we have this different responses, and this is the sea surface temperature response for slab ocean and the fully coupled model. So bottom is the fully coupled model, and what I saw is this large cooling around 40 degrees in North Pacific. So we looked at the ocean response, and what we found is that for June perihelion, summer is hotter, but winter is colder as well. And the subsurface water temperature is determined by the cold season temperature. As a result, we have this purple blob that has low cold anomaly for June perihelion, and as a result, there's less heat transport to the north, and this made this region fairly cold. So what at least the model results suggest that it's possible to have large local precipitation change as a result of changing precessional cycle. So, I mean, the question is, what will be the response of the isotopes? So, because we already have the ICSM available, so I ran ICSM forced by GFDL SST, and this is the results. Again, this is the precipitation difference. The top is precipitation difference, and the bottom is the isotope difference. Unfortunately, there is a large change in precipitation, but the direction is the opposite. So there's actually less precipitation for the hot summer case, and and vice versa. but at least, what this results this result confirms is that the regions where I expect very high, regions where I have very large change in the isotopes have relatively large precipitation change. So what you see is that, over the Asian monsoon region, East Asian monsoon region, there's a large increase in precipitation, decrease in precipitation, and an increase in the isotope values. So I added isotopes into the GFDL model. So I mean, just I went through the code and tried to find where water is changing and follow the water cycle. So as was previous talk, what I found is that handling small values are difficult, and there are so many if statements. Mass is not conserved. I mean, mass is actually forced to be conserved. So there are a lot of places that that mass is not really conserved. So there are a lot of decision-making process, and then especially, and then there are a lot of places where I don't know. I know the final water values, but then exactly where it's coming from and where it ends is not actually very clear. So those are the kind of difficulties that I ran into. And what I thought was that if the person who is working on isotopes work closely with the model developer, some of these problems can be actually solved relatively easily. And this is the first month result. So this is first month, I initialized with very low values because water vapor, it's a very fast process. So usually after a couple of months, we don't really see the influence of initialization much, except very dry or very cold regions. And then Jesse mentioned that the difficulties with adding isotopes into the land model. So I started with the atmosphere model. So I'm done with the atmosphere model, and for the land model, currently I fixed the isotope flux, and I'm probably as a first step, I'm going to use bucket-like model with the land model. Okay, that's it. Thank you.
Great, thank you. I think we should open up questions to our speakers to start. There are two polls. The first one I already distributed to gauge community interest of legacy model versions. And then there's another poll which I will distribute after our first round of questions to gauge community interest for ICESM 3. John, can you put up the slides? So,
if you can ask a quick question first.
Oh yeah, go ahead.
It's for Junyuan. Do you have any plan for the ocean model? I know that it is small and will be shared with the NCA CESM model.
So currently, this is funded through NSF P2C2, and I was funded to add isotopes into the atmosphere model. So right now I don't, because as we've been telling throughout the day, having high resolution model and all these things are very, very helpful. But sometimes working with ocean model and everything is actually pretty time consuming. So right now I don't, but if if we are successful in adding isotopes into the land model pretty quickly, and then, I get all the results. So this is our project year 2. So it started a year and a half ago. So I have at least a year and a half to finish the project, and I'm expecting that I'll probably be able to add isotopes like within several months. And if that becomes possible, then maybe like I can spend next year at least thinking about adding isotopes into the ocean model.
Thank you.
Great. Eric has your hand up. Do you have a question?
Yeah, thanks. I guess I want to follow up a little bit on Jesse's comments about what I think you're saying is that there's a need to refactor some of the isotope schemes so that they're compatible with the new versions of the models. And if I'm understanding you right, you're referring to this common community physics package sort of interface that has to be used in order for any of the parameterizations to be compatible with the sort of new versions of the model. Could you talk a little bit about that? Because I guess I'm getting a little concerned that I don't really know the scope of the problem of moving all of the different schemes over to the new formulation.
Yeah, sorry, I guess it can be, so the CDBP stuff is a little independent, although you're right that, whatever isotope schemes we have would need to be CCPPized to work with the new physics, but this is more in that, well, really, it's a problem with convective schemes. So in order to get the water isotopes simulated properly, we kind of need them in the guts of, so to speak, of the convective scheme, because we need to know not only like the phase changes that are happening, but then also, there's vertical motion. And so we need to be tracking that like every step of the way to make sure that our sources are the same. And so, so that's kind of the issue, is how can we get isotope code into like the core of these physics scheme, whether they're CDBPIs or not. And then kind of keep them there. So, because a lot of times we'll get them in to a version of it, but then, oh, now there's the new version and we've lost the isotopes completely. And so someone has to spend time doing that again. And that's the same issue with the land. I don't know, I'm not as informed about the land model. My understanding is that's the same problem, because basically they just, from going from CLM4 to CLM5, they changed the physics schemes involved with moving water through the soil column, and so that kind of broke the isotopes there, and so we would have to re-implement that. So just how can we keep it so then when like CLM6 or whatever comes in, that they just keep the isotopes instead of having to redo that? Does that help? Sorry.
Yeah, I mean, we do sort of I haven't kept track of it, but I mean, Jung Yun is mentioning support that came from the Paleoclimate program, and our program is funding Nick Seiler and Rich Fiorello to work on these things. And the hope when you make those kinds of awards is that you do this thing once and then it becomes a community resource thereafter. I guess it hadn't really occurred to me that there's a maintenance issue there that needs some following up. So what the sort of risk matrix is there, and what can be done about it, I guess, is kind of a concern.
Right. Adam, you want to ask your question? I think I just saw Adam Harrington has his hands up.
I'm sorry, can I defer to Bill's question, as that's more relevant to the conversation taking place?
Oh yeah, sure. Yeah, I think Bill has a question.
Yeah, I was going to follow up from the land perspective, and I apologize. I somehow managed to not register for this. It didn't have the link until just now, so I missed the talk. So maybe some of this was already addressed. But from the land side, the issue was that the isotopes had been implemented in a kind of one-off way that that was there was a whole sort of parallel isotope scheme. So as Jesse said, when there was new model physics, that the model physics got out of sync with the isotope scheme. And so the approach on the land side has been to rewrite much of the land hydrology code to be more amenable to have isotopes fit in so that they would be maintainable long term. I think that's sort of addressing Eric's point, so that it could be done once and more of a once and done sort of effort. But that does involve a very large rewrite of the land code. So it's a large upfront effort to have that long-term maintainability.
Is it okay if I ask my question now?
Go ahead.
So Jesse, well, everybody, just so you guys know, CSLAM advection is not currently supported in the variable resolution configuration, and there's no current resources allocated to do that. But your results show that default SE advection is problematic for isotopes. Do you think there's any opportunity to, in the short term and before we maybe improve the advection scheme in VARES, to could we do some sort of mass fixers? Do you think that there is a pathway there to be able to use the SE advection scheme with isotopes?
Well, actually, I should let John speak, but basically that's what we are doing for the IHES, the isotope enabled IHES version. So we have extra mass fixers to be like, oh, are you going off the rails? Then come back on the rails. So it seems, well, I guess we'll let John speak, but it seems to be working.
Yeah,
Okay.
so right now we have mass fixers in the SE configuration to restore the bad values to realistic values. And I want to add one more point, that it's not only the advection scheme, the dichrome matters. The macrophysics, like Jesse has mentioned, matters a lot. So I tested different schemes in the CAM6 configuration. And what I found was that the MG2 updated macrophysics is much better than the MG1 in terms of precipitation delta 18O. So basically repeat what Jesse has said.
Well, are you saying you had some false alarms that you attributed to the SE advection scheme when it could in fact have been the MG1 scheme?
I mean, the dichrome certainly matters, and the macrophysics also matters. They both help to improve the delta 18O in precipitation.
Okay, so dichrome still matters. Got it.
I think Eric has his hand up again.
Yeah, sorry, just something else that Jesse said. He was suggesting that the MPAS dicore has some traction, and are there kind of big concerns about things having to be sort of done differently in MPAS versus SE?
Well, usually actually putting isotopes into a dicore is not too hard because they almost always have some sort of effective scheme, and so and from a dicore standpoint, the water isotope tracer is just viewed as a generic tracer. So I mean, you always, it takes a little bit of work, but I don't view it as a deal breaker, so to speak. So,
yeah, there's no conservation issue or things like that, right?
I mean, yeah, not that. If there was one, it should show up already in other tracers. It wouldn't be isotope specific.
Right. And is CSLAM specific to the spectral element dicore?
I think
Yes.
so. Adam can comment.
Yes, it is.
Okay, thanks.
Great. I think we can migrate to our discussion. Actually, the poll about I'll just talk a little bit about the poll results. So people seems to be like 62% of people over versus 48% people who are interested in still maintaining the the ICSM 1.2, like Jesse mentioned, so this is not going to be an NCAR effort, but I think as a community, we can probably make this happen. And of course, with the help of Jesse and John, reach out. Yeah, so if people are still interested, I think this is something we probably should do. The other poll I did look at how whether people are interested in ICSM 3, and it's overwhelming, like 100% people saying they're very highly interested in ICSM 3. I'm personally very interested in this new model development as well. And I was wondering, we could talk a little bit or discuss a little bit about potential pathways. I know Jesse had some slides that he had some questions and some pathways in the slides that he didn't finish. So Jesse, do you want to finish the part that you proposed for a pathway to develop CESM 3? And we can also, there's also a question in the chat asked by Clay, which also relates to like potential collaborations or questions that we could propose for the development of ICSM 3.
Yeah, sure. Sorry, I'm bringing it back up again. And yeah, and apologize for going over, like way over. So hopefully I didn't like crowd into your time. Sorry, let me get back to, yeah, there we go. Whoops. So sorry, the bottom question is kind of going, I guess, to Eric Weir's one of how do we provide long-term maintainability? And it's kind of been three methods that I've heard kind of seriously talked about. So one is having the isotope physics completely outside of the parameterization. So we ignore the convective. I'm picking on convection again, but ignoring the kind of convective transport and just saying, well, we get the tendencies, let's just approximate them and then solve for the isotope values. So that could work. I mean, in some ways we know it will be an approximation, so we know it won't be exact. But what I don't know is how large that approximation is. It could be, if it's a small difference, then maybe this is totally the way to go. If it's a large difference, it might not be. Ultimately, I think that will take like actual kind of science work. Someone will have to take a fully isotope and like in the guts version of an isotope model, and then this kind of pulled out version and just see what the difference is. My suspicion is that it'll work well for D18O or delta D, but it will not work well for things like DXS, just because it's a second order quantity. But I don't know that. That's just a guess. The second one is it's kind of changing the way we view how parameterizations work. So in the sense that you could imagine that for something like, say, a phase change, instead of the parameterization internally just saying, oh, this is how I'm going to do a phase change, the model has this kind of, and this is maybe where CCBP gets involved, which we can talk about later, but you can imagine there is just one scheme that manages phase changes, because in some ways, from a physics standpoint, it's the same physics every time. It should be. So, so you can imagine if you did that and it had this sort of object that's, I'm thinking of a software object that can manage that, then it can manage all the isotope physics because that's when fractionation occurs. And so then it would be much easier for new parameterizations to incorporate isotopes, because basically they would just call, calculate a phase change, and then this thing would handle the isotopes and they wouldn't have to worry about it. And then the third one is machine learning, and I realize machine learning, sometimes just gets tossed around, but there actually has been, in fact, I think the Hadley Center model just came out with a paper where they have done exactly this. They've tried to use a machine learning algorithm to emulate what the isotope values would be by using their isotope enabled version of the model. And it seemed to show promise, but again, it's one of those things where like it works well. It seems to do really well in some situations and not well in others. And it's also unclear if you'd have to retrain the machine learning algorithm every single time a new model came out. So, but it's just a possible avenue. So yeah, that's all I had as possible discussion. I guess I can stop sharing, keep sharing. I'll stop sharing.
Interesting. I guess we're at the break time. So if you want to go get coffee and tea, feel free to do so. And if you want to stay for the discussion, we can continue the conversation. Yeah, thanks everybody for participating in the water isotope session. Our next session is going to be chaired by John. Am I right? On the biogeochemistry.
It'll be the vegetation
Oh, the
section.
vegetation session. Oh,
Yeah.
sorry. My bad. Actually, I had a quick question for Jun and for Jesse and John as well. So what type of question do you guys think would be most appropriate or would be most advantageous for CESM3 or ICESM3 to address?
So is it, for particularly for this, I mean, for paleo group, or is it like, what kind of questions that, isotope enabled are good questions for the isotope enabled models to think about solving?
Or I guess I should be more explicit. So we already have those many versions of isotope-enabled models, right? Seems like the new versions of models, they're better in model physics. They have the capability to run like at higher resolution and things like that. So what do you guys think would be a good question that makes the most use of those newest model development?
So what I've been thinking about was like, the difficulties using the isotope enabled model has been like, what kind of additional information that, isotope enabled models can tell us, right? And for paleo, it's obvious because, paleo proxies are the, one of the most important proxies are the isotopes. For modern applications, some of the things that, I've been thinking about was that, like, there are a lot of like, processes in convection, like, how much detrainment is happening and what's the role of the, cold pool, rain re-evaporation. So those are the kind of questions that, that relatively low resolution model cannot, relatively low resolution model or models without prognostic, precipitation did not have, was not able, were not able to answer. So for me, like, especially with the advent of high resolution and variable resolution, I mean, looks like now we can actually run the model with in a very high resolution. So now I think, we may be able to actually resolve convection, and in this case, we might be able to actually think about, how isotopes can help us better understand the convective processes. So those are the kind of things that, I was thinking about, especially related with the new development. The difficulty with the paleo, with the new models currently, I haven't actually, looked very carefully up on like, higher on more recent version of the model, but then, some of the things like climate sensitivity and the ability to run the model for a relatively long period of time. So that's why I think, at least for now, if I mean, my student is using CSM 1.2 because that seems to, fit our needs best. Mm-hmm. So in that way, I mean, for paleo, I mean, it's great to have like, high resolution, many more processes, but at the same time, being able to run for a long time, that's actually a very, in a relatively short time, that's actually very, very important. So I actually would like to ask you to like, keep supporting maybe something like 2 degree by 2 degree, kind of, model configuration.
Yeah. Yeah, makes sense. And I
has been
have some response or have things to add.
Yeah, June has summarized this very nicely. One capability I want to add is the water tagging capability Jesse has development. So with this capability, you can track the movement of water in the land, in the atmosphere system. So with this capability, we can study the hydrological processes. And I think that's an exciting tool to use for the climate dynamics community, as well for the paleo community, for us to better understand and interpret the proxy records.
I think Adam has his hands up.
Yeah, sorry, I'm talking so much today, guys. You know, I've heard this request to support a 2-degree grid from the paleo groups for a number of years now. And at the same time, I've also been thinking to myself, it would be so nice if we had a LGM comp set that would run out of the box in CSM3. And so one way to really plant your foot on this 2-degree grid is maybe to develop a 2-degree LGM comp set that would run in CSM3. I think if you got started on that you could actually get it in time before the code freeze. And I think that would really help us integrate the paleo needs with the latest, greatest version of CSM. And it sort of grandfathers you in, because now you have a comp set, we have regression tests, we can't let it break once it's in there. And to be honest, the hardest thing about paleo is generating all these different coastline files, different ocean files, and all that stuff. That's turns off a lot of people from wanting to even do paleo runs. So I think the low-hanging fruit here is to get a LGM comp set or any configuration in the past, just to get one in there, let it be 2 degrees. And I think that would be, it just seems like a smart move in my opinion.
Yeah, Betty had her hands up.
Yes, just for Adam, actually in the development of CESM3, LGM will be part of the development at whatever resolution they have. We'll probably have to do some thoughts on how to spin it up in that, but I think what we learned with CESM2 is you need to push the model outside its historical view, and because things just when you push it outside don't work. LGM got too cold in LGM2, or for LGM in CSM2. But you're right, a lower resolution model is something we've been thinking about, the fast CSM, not just for paleo, for people that want to run long ice climate coupling of the ice sheets. And biogeochemistry, there's a lot of reasons to have a faster version of CESM3 as we go forward. So we have been thinking about that and talking to the community and the universities. You know, besides resolution, what else could be done to make it really fast? Can we get to 100 years per day? Or I'm always hoping for 200. But because then you can run way more things. And that's where CSM3 is going to be nice too. It will have not only the Greenland ice sheet, but now the Antarctic ice sheet as a capability of coupling. So not so much related to isotopes, but just in general, CSM3 is going to have some new features that I think paleoclimate is going to like.
Okay, I didn't know you planned on putting an LGM comp set in. I haven't seen any movement on that. I think it's
well, the model's not ready yet. Yeah. So, but
yeah, I mean, we can also put in a pricing one if anybody's interested in helping me. All right, so I think we should start the next section.
Okay. Thank you, everyone. The next session is the vegetation session. we should just get started right away. But I also would like to point your attention to the Jamboard. You can fill out the discussion questions there at the time that works best for you, and also for previous sessions. So please take a look at the Jamboard to include your input. Let's get started with our first invited speaker for the vegetation session. I want to welcome Jenny Kowalczyk to discuss her research. She's a postdoc at Brown University. So feel free to share your screen.
All right, thank you. Let me find my presentation here. Okay, can everybody see my slides? All right. Hi, everyone. I'm Jenny Kowalczyk. I'm a postdoc at Brown University, and thank you very much to the organizers for having me today. I'm going to be talking about some work from my dissertation on precipitation and vegetation in a high CO2 world. I apologize, I did change the title a little bit from what's in the agenda, but I promise that I will be talking about climate vegetation feedbacks as well. And this is work I've done with Jung-Un Lee, who we just heard from, who is my advisor, and Jiang-Ju Nkar. There we go. So the big picture questions that motivate my research, the first question I'm interested in is to what extent can the early Eocene be a climate analog for our future climate under a high emission scenario? And specifically thinking about climate and vegetation, I want to ask if projections of drying and browning for the future under high emission scenarios are compatible with the lush plant fossil record from the early Eocene. And the second big question I'm interested in is basically, are we modeling precipitation correctly for a high CO2 world? And specifically, how can we improve model proxy agreement for the early Eocene? And I investigate these questions with climate modeling, including dynamic vegetation. And I think that modeling with dynamic vegetation is really important for several reasons. One, the precipitation proxies for the early Eocene are based on plant fossils. And modeling with dynamic vegetation allows us to directly compare our results with the plant fossil record. This has been, I think, an understudied area. As far as I know, there's only been one previous study published for the early Eocene with dynamic vegetation modeling and a fully coupled land atmosphere configuration by Lopston and others in 2014. And it's important to have dynamic vegetation modeling so that we're fully including climate vegetation feedbacks. So some important climate vegetation feedbacks, the CO2 fertilization effect. So at higher concentrations of atmospheric CO2, it's easier for plants to assimilate carbon. This allows them to operate with increased water use efficiency of C3 plants. And that can allow vegetation to expand in arid regions. So this figure here is from some simulations we did with present day geography. And it's showing total vegetated area versus mean annual precipitation. The green line is from a simulation with 4 times pre-industrial CO2 and CO2 fertilization versus the red line, which is warming only with no CO2 fertilization. And we can see that in drier regions, the simulation with CO2 fertilization has more vegetation. And this has also been observed, this expansion of vegetation into arid regions has also been observed in the real world in the past few decades through satellite observations. And changes in vegetation can feedback on climate and precipitation through feedbacks involving transpiration and the albedo. So the transpiration feedback is important in places like the present day Amazon, where a lot of the precipitation is coming from recycled water from transpiration. So in effect, the rainforest is helping to engineer its own favorable climate. And the albedo feedback can be important for both temperature and rainfall. One example where it's thought to be important for rainfall would be North Africa during Green Sahara periods. So I'm going to tell present two like mini stories here from my work. The first is focused on North America. And this was motivated by wanting to understand the apparent discrepancy between the widespread drying projected for summers in the future under a high emission scenario. It's shown in this map here. In contrast to what plant fossil evidence tells us for the early Eocene, that the continental interior was lushly forested with high precipitation. So with Jing's help, I ran simulations using present day and early Eocene geography with 3 times pre-industrial CO2. And here I'm looking at the seasonality of precipitation over North America. And we can see that in the early Eocene, we have a strong summer monsoon, whereas we don't see that with present day geography. And looking at the dynamic vegetation results, we see divergent responses to increase CO2 for the 2 geography cases. So with the present day geography, with increasing CO2, we lose these forests in the west, and there's only a moderate expansion of forested area into the interior here. Whereas with the Eocene geography, we have a greater forest coverage, and with increasing CO2, the forest coverage expands. And coming back to climate vegetation feedbacks, we show that the greater forest coverage in the early Eocene case increases the summer rainfall via the transpiration feedback. And I did that by running additional simulations where I set transpiration to 0 in these areas in the boxes. I have like a larger area and smaller area case. And these plots are showing the change in summer precipitation in these 0 transpiration cases. And you can see that it decreases by up to 50% in the continental interior. So this is telling us that this transpiration feedback could have been important to maintaining the summer monsoon over North America in the early Eocene. And then the second little mini story I'll present is how thinking about how orbital configuration affects early Eocene rainfall in the tropics and subtropics. This work was motivated by this model proxy comparison study that came out recently. So this plot is showing the deep MIP multi-model means for precipitation at different CO2 values compared to proxy data in these little circles. And this is from the Deep MIP project. And we can see that in some areas, there's a discrepancy between the model precipitation and the proxy data. For example, here, I don't know if you can see, but in this subtropical Asian region, the model looks too dry. And so, and the DMIP simulations are done with a present day orbital configuration. So we wanted to see if using a different orbital configuration, for example, one with perihelion occurring in June, how that would affect the tropical and subtropical rainfall, and if that could help reduce this model proxy discrepancy. So for this, I ran simulations for the early Eocene with perihelion in June and in December at high eccentricity. And these figures here are showing the mean annual precipitation results. So the top panels are the absolute values for December and June. And on the bottom, we have the percent difference and absolute difference in June minus December. And so we found that precession can change the mean annual precipitation by up to 7 centimeters a year in some areas, but unfortunately, it didn't resolve the model proxy mismatch over Western Asia. So we can see here in the June perihelion case, it's still too dry here. But we do see that the June perihelion has a significant effect on the modeled vegetation. We found that the shrubland area expands by over 10% in the June perihelion case that's shown in this bottom figure here. And thinking big picture about this, we realized that the global plant fossil record is integrated over orbital cycles. So what we should be doing is combining results from these end member precession simulations to assess how well the model is doing reproducing early Eocene vegetation patterns. So these figures are showing the combined results. On the top panel, I just have it broken down by vegetation type. And then in the bottom figure here, I've combined that into a biome map. And just to drive this point home, if we compare the biome map from a single orbital configuration, in this case, I chose December perihelion, versus the combined results, we can see that if we were looking only at December, we'd be underestimating the vegetation coverage in the southern hemisphere. And so then we can compare our combined results to the fossil compilation shown here on the right. So this compilation is comprised of over 100 fossil localities around the globe. And in this figure, the blue and dark green colors are tropical rainforests. The like bright green here, or neon green, is seasonally dry vegetation, like similar to the Mediterranean today. The darker, or the middle green, I think, is paratropical forest, and then the brown and red is temperate forest. So comparing to our modeled vegetation results, we see that in some areas the model is doing really well. Like, for example, over equatorial Africa and India here, in South America, compared to where there are fossil data, the model is doing really well in North America and Europe. But then there are places where high latitudes, for example, the model is not producing temperate forest. It's still too cold and dry. And I will note that compared to simulations with the fixed vegetation map, where vegetation is prescribed for the high latitudes, the climate that I get with the dynamic vegetation is colder. So it's kind of like, do we need the warmth first or the vegetation first? You know. And then we can also see in some subtropical areas, the model is too dry. Like I mentioned here, for this region in Asia, nothing is growing there because the model is too dry. And also for these coastal sites in North Africa, the model is very dry there too as well. So to summarize, I haven't kept track of time, but I think I probably talked fast. To summarize, I think that modeling with dynamic vegetation is important because at high CO2, the CO2 fertilization effect shifts where vegetation is growing in climate space. And we also know that vegetation affects climate through transpiration and albedo feedbacks. So everybody should be including dynamic vegetation in their modeling. And then I showed that the transpiration feedback might have been crucial to maintaining the North American summer monsoon in the early Eocene. And then thinking about orbital configuration, we found that unfortunately simulation with June perihelion didn't really help that model proxy rainfall mismatch in the subtropical Asian region. But we do see that combining vegetation modeling results from these orbital precession end members improves the match to the fossil record. And our comparison to the fossil record suggests that the modeled climate is still too cold and dry at high latitudes and too dry in some subtropical areas. So thank you for listening, and I probably have time for questions.
Thank you. Oh yeah, Clay, you have a question?
Yeah, nice talk. I was curious because I played around with the dynamic vegetation probably too much. And it's sometimes an inability to capture vegetation coverage. I was wondering if you made any changes or how you spun things up.
Yeah, I forgot to mention the only change I made for the Eocene cases was I removed the C4 plant functional type. And then the simulations were initialized from bare ground. So I had to run it for about 500 years before the boreal forests were the slowest, which I mean shouldn't be there in the Eocene anyway, but because it's too cold at high latitudes, they're happening.
All right, thanks. Yeah. Yeah, I'd be happy to talk more offline at some time about some of the technical.
Yeah, I'd be really
changes.
interested in that. You know, I thought about messing around with you know, some of the parameters for the other plant functional types, like you know, establishment temperatures, or you know, I mean, but I decided to just try. You know, I think the removing the C4 plants, there's like that's pretty solid, and then other things you could argue for, but I decided not to mess around with it more for my first try here.
Yeah, sounds good. I know nitrogen deposition in CLM4 can be kind of important too sometimes, so worth checking out. Thanks.
Yes, Young, you have a quick question?
Yeah. Yes, so it's clarification question. So in Junyuan's talk, she showed that the ocean dynamics matter. You run fully coupled simulation against slab ocean, you'll see different response over the East Asia. I'm wondering in your Eocene simulation, whether it's slab ocean or fully coupled.
Yeah, that's a good question. So it is slab ocean, and I think it would be really interesting to try fully coupled and see if that helps the problem.
Okay, great. Let's move on. If you have remaining questions, let's keep it to the discussion. Unless Samaya, do you want to ask a quick question right now? Or is this okay for a discussion point? Just want to make sure I'm not. Okay, good. I don't want to neglect anyone's. Okay. We'll keep it for the discussion, move on to our next speaker to stay on time relatively. Happy to introduce our next speaker. Adriana Foster is a project scientist in the terrestrial sciences section at NCAR.
Thanks. Can you guys see my slides and everything? Okay. All right. Yeah. So thanks for giving me the opportunity to speak. So this is a map of Landsat-derived greening and browning trends for Canada and Alaska. And we can see these broad changes in productivity, which we know are accompanied by finer scale changes in vegetation structure, composition, and biogeochemical cycling. And so my work so far has focused on understanding how these fine scale vegetation changes interact with one another, as well as how we can use ecological modeling to better understand these interactions. And so specifically, I currently develop and apply the cohort model FATES. So FATES is a vegetation demographics model that operates inside CLM. So this means that it breaks vegetation up by cohorts of similar size and PFT. And so these cohorts grow and die on patches of a similar age, and then atmosphere fluxes are simulated on a 30-minute time step, whereas plant growth and allocation occurs daily. And so, you know, why is this important for studying ecological interactions? Well, with a model like FATES, we are necessarily in the business of capturing ecological processes at multiple scales. So we've got cell level processes of photosynthesis, leaf level processes like stomatal conductance and impact on boundary layer dynamics. We also have tree and stand level processes like allocation to different plant tissues and competition for resources, and then also impacts on soil and atmospheric columns. And then we can, of course, scale this up to model vegetation dynamics globally. And we know that at each of these scales, vegetation influences and interacts with its environment to feed back to site and soil conditions, biogeochemical cycling, and climate. So for example, in boreal North America, we know that we have these fire, vegetation, soil interactions that create lasting legacies of alternative forest types. So for example, black spruce forests tend to grow on soils with a thick organic layer, which leads to cold, moist soils, slow decomposition, and high moss growth, which leads to the persistence of these types of stands. Whereas higher biomass white spruce and deciduous stands tend to grow on more shallow, well-drained soils with rapid decomposition, little moss growth, and the persistence of these forests. And then fire severity and the subsequent depth of burn leads to direct impacts on post-fire regeneration. So higher severity and greater depths of burn leads to more deciduous recruitment following fire, whereas less burning leads to coniferous recruitment following fire. And then changes in these dynamics, either in the past or the future, can have wide-ranging consequences on regional soil and vegetation conditions, as well as climate and disturbance regimes. So for example, we know that evergreen forests have a lower albedo than do deciduous forests. And so this figure on the right is from a study by Beck et al. Looking at post-fire winter and summer albedo for a high severity burn, which resulted in a shift to a deciduous stand, and then a lower severity burn, which did not result in a shift. And so we can see that the albedo in the winter and in the summer is higher for the deciduous stand. And so a shift towards higher deciduous fraction could lead to a cooling effect on the landscape. And then in contrast, we also know that forest cover has a lower albedo than does tundra. So we know that past or future changes in the northern tree line, for example, also has the capacity to feed back to climate. And so these vegetation feedbacks can be simulated in Earth system models. And in fact, when you include them, they can improve model performance when compared to observational data. So here's an example from some work I did with a similar model to FATES, looking at modeling vegetation dynamics in interior Alaska. And so for this work, I eventually ended up adding permafrost dynamics to the model. I updated the nutrient dynamics and then also updated wildfire dynamics to include burning of the organic layer. And so here is what is supposed to be a black spruce site based on the inventory data. But then if we look at the model data, before I did any of these updates, we were not predicting either the correct biomass or species composition. After adding just the permafrost dynamics, the species composition looks better, but we're still over predicting biomass. And then after adding all of those updates, we're now capturing both the biomass and the species composition accurately. So the model required this linkage between the above and below ground dynamics for the system to be fully simulated. And so I've been doing some similar work with FATES at point locations across the US at sites maintained by the National Ecological Observatory Network, or NEON. And so these sites have information on forest structure and composition, as well as soil conditions and flux dynamics. And so for today, I'd like to focus on Bonanza Creek, Alaska, which is an interior boreal site. Okay, so this is inventory measured basal area colored by plant functional type for plots at Bonanza Creek. And so in FATES, we have the option to combine species into our own plant functional types. So here I've designated birch and aspen as one deciduous PFT and white spruce as a spruce, black and white spruce as a spruce PFT, and then larch as its own PFT. And so then here is FATES output of basal area initiating from bare ground in 1914 and continuing until 2014. And so, we can see that the total basal area is about right, but we're completely missing the birch and aspen, and perhaps due to issues with not representing topographic variability. So remember, I said we have these differing forest types in Alaska, where we have black spruce forests on cold, moist soils, which tend to be in lowland areas. And then we have the deciduous and white spruce forest types, which tend to grow on more shallow, drier soils, which tend to occur in upland areas. And And so here's a picture I found that was taken at Bonanza Creek, and you can see this scrubby black spruce in the foreground, which is kind of in a lowland area, I think. And then you can see in the background this dense stand of deciduous forest, which is kind of in an upland area. And so this, corresponds with those differences in basal area and species composition that we see in these inventory plots. And so here's a comparison of volumetric soil moisture observed at Bonanza Creek on the right, and then that simulated by CLM Fates on the left. So on the y-axis or the x-axis, we have time. This is just for 2019, and the y-axis is soil depth. So CLM seems to be simulating a much wetter soil column than the NEON observations show. And then this is a similar plot for soil temperature. So here it seems that CLM is simulating a warmer soil environment than the NEON observations show. And so we've got this mismatch in the simulated site conditions that's leading to a mismatch in the forest conditions, or probably vice versa. And we have these interactions going on that are not being captured by the model. And so Sean Swenson's hill slope hydrology within CLM allows for hill slope specific modeling of vegetation and soil conditions. And so here each column is defined by its soil position, and then water can flow between the columns. And so I'm hoping to use Fates hill slope at these NEON sites, which I think will improve simulation of below ground conditions. And so I'd like to propose that we can also use Fates to conduct similar studies with paleoclimate and ecology. So at multiple scales, these ecosystems are being controlled by long-term temporal processes, which we can simulate with models like CTSM. And indeed, vegetation demographic models like Fates have been tested on their ability to hindcast forest responses to past climate change. So here on the left, for example, is vegetation determined by pollen records of Eastern North America during the late Quaternary period. This large crosshatched region is the ice sheet. And then researchers used a forest demographics model to predict the past vegetation for this area and quaternary landscapes, and compared output to the pollen record. And so given the outcome at Fates, testing Fates at the point and regional scale during historical time periods, we can further improve the model. Gordon Bonin also used a demographic model to reconstruct the composition of forests in Eastern Virginia under historic climate. And they also found from their comparison to pollen data that the relationship of tree growth to temperature in the model needed to be improved. And so we can also use, these paleo simulations to improve models like Fates. However, because Fates is multi-scale in nature, and the fact that these scales often interact non-linearly with one another, it can be really difficult to calibrate across scales all at once without hypertuning into some kind of rabbit hole. So for example, while trying to calibrate output of, say, GPP or transpiration, we also have to ensure we capture the correct leaf area, the stand structure, recruitment and mortality, as well as PFT composition. And so ideally, we'd like to control for some of these processes while we aim to better parameterize and calibrate others. And so in Fates, we do have the ability to control for more complex processes. So the Fates team has been working on developing these reduced complexity modes for Fates. So, we've got full Fates with sort of all the processes on. But then we also have satellite phenology mode, much like in CLM BGC satellite phenology mode. We used observed LAI over time for each PFT, and then each PFT is on one patch. And so we essentially turn off growth, disturbance, and mortality. We also have no competition mode, where these PFTs are given a fixed area to grow, but don't compete with one another. And then we also have prescribed biogeography mode, where we allow for growth, disturbance, and competition, but only we restrict the PFT establishment and growth to where they actually occur. And so the Fates team have been working on this concept of a calibration cascade to test various parts and parameters within the model using these different reduced complexity modes. The idea being that the model would be improved with each subsequent calibration step. And so the first step is to do it in SP mode. And one of our initial questions was, what parameters are actually important in this mode? And so the objectives of this first step is to conduct a perturbed parameter experiment, or PPE, to check on which parameters have any amount of impact in this mode, as well as the importance of those parameters. And so luckily I'm able to borrow really heavily from this ongoing CLN PPE project. And so initially I'm conducting a one at a time min-max sensitivity experiment. And I'm also using this sparse grid to save on time, which these 400 grid cells were chosen based on representativeness and responsiveness to climate and environmental change. And so for this test, I looked at all the FATES parameters. This was 117, which included those related to photosynthesis, radiation, leaf traits, among other things. But I actually expected most of these parameters to have absolutely no effect on model output in SP mode. And so I really only expected those related to photosynthesis, radiation, and leaf traits to be effective. And so of the 117 parameters, only 36 had an impact in this mode. And so for impact, I was looking at history output of GPP, transpiration, and soil conditions, and albedo. And so as I expected, most of the important parameters had to do with leaf traits and radiation. And so here's just looking, oh, thank you. Here's looking at grid cell averaged GPP across all the parameter simulations that had any impact. So I'm showing annual GPP on the left and then interannual variability on the right. And so there are quite a few that only like very slightly modified GPP, but we do have some outliers. So VC max is pretty important. We also have the clumping index, and then these theta CJ curvature parameters are also pretty important. And so here are just the top 20 that affected GPP. And again, we see mostly leaf and radiation parameters. And so we can use these important parameters to start the calibration process first in SP mode, and then moving on down this calibration cascade. And so, currently we're experiencing a boom in remote sensing technology and advancements, allowing for these high resolution observations of vegetation characteristics and scale, now and into the future. And so I spend a lot of time working on how to use these new observations to benchmark FATES, but we can also use data on past vegetation and climate, which can not only increase our confidence in how the model would function under a novel future climate, but also further our understanding of vegetation and climate interactions. And then also, I think it would just be really cool to try to model these giant lycopods of the Carboniferous period. And yeah, with that, I would like to thank my many collaborators among TSS and the FATES team. And yeah, hopefully I have some time for questions. Thank you.
Thank you. Maybe it would make the most sense if anyone has immediate questions for Adriana's talk before moving on to other topics. Yes, Ran.
I have a quick question for Adriana. Maybe I missed this, but is there a region dependency of the scale of FATES? Are there particular regions that it doesn't really work well?
Yeah, we're still, so I would say that we're still in the testing and development phase of FATES for most of the globe. My colleague, Jackie Schumann, has done a lot of work in the tropics. So she has got some pan-tropical runs that look really good against data. And then a lot of the other work is being done at point scales in the tropics. And then we've also got a lot of work going on in like California area. And then some of my work is focusing right now on boreal and temperate US. So yeah, I would say that the field is open to be improved for sure. Yeah.
Thank you.
Yes, Sumaya, you have a question, comment?
I do have a question. Thanks, Adriana, for the talk. My question relates to the allocation. There are two different questions. You talked about the temporal resolution for allocation, which is daily.
Yeah.
I'm just curious if you looked at it at a different temporal scale, and if that improves the skills of GPP prediction.
I don't believe we have, I have not looked at that, and I don't know if others have. I would say that, I think, maybe if we're allocating to leaves on a hat, sub-daily time step, that might improve, but I would think, you know, as kind of at some point, you know, like how long does it take trees to change their allocation, I guess.
Yeah.
In real life, you know. But yeah, I agree. Like, yeah, I think, you know, and there are other aspects of fates that, you know, I think might improve. GPP could be like our phenology scheme. I think, you know, we could do better there. Yeah, so yes, that's a good thought though. And so that's certainly something we could try. Yeah.
Thank you. Can I follow up just with a quick question on the allocation? And I was just curious how it would vary depending on your climate zone, right? Say in the US Southwest, what would the allocation scheme and resolution would be compared to wet Eastern United States?
Yeah, so currently our allocation is dependent on sort of the allometry that you set up, and then how it's sort of a PFT level and all these PFT level parameters. So you could certainly modify how, if you have a PFT, you know, for the Southwest US versus a more a wetter environment, you could certainly have different PFTs for those regions that would respond differently to in their allocation and allometry.
Thank you.
Yeah.
I'm sorry, I think I missed your question in the chat about stomatal density and other photosynthesis limitations. Was that was probably for me?
Oh yeah, let me stop.
So I think stomatal density isn't directly parameterized in the CLM4 CNDV, but it's the resistance is inversely proportional to atmospheric CO2. So at high CO2, it's higher. I might have said that backwards. Conductance is lower at high CO2. And then for light limitation, the way the photosynthesis is calculated, it's the minimum of the light limited and Rubisco limited rates. So does that answer?
Yes, thanks,
Okay.
Jennifer. Yeah.
Yes, John Goon, you have a question?
Yeah, I have a very quick question. So to Adriana, so from your plots, looks like you started the model with bare ground. So are you planning to, or do you have the capability of starting with, like, you know, some initial file or something like that? Because, you know, that can be done, but, like, you know, especially for starting, you know, graduate student, it's something that's very, very difficult. So I'm curious, what's your plan?
It's actually, I think it's at least, well, I shouldn't say this, but we try to make it easy in Fates to do this. So, but yes, you can start with initial stand structure. So there is a file that you can pull, you know, basically saying there's these cohorts, so these trees, number of trees between this DBH and that DBH, or this type of DBH and this PFT. And it initializes the model. And so actually I have done that at the NEON sites, and it's much improved when you do that, when you rather than running it from bare ground. Yeah, so that's definitely a way to, you know, if you're really interested in like the next like 5 to 30 years, like I would say, yeah, initialize with known current conditions. Yeah.
Thank you.
Yes, Betty.
So Adriana, if someone came to us, let's say Jenny, and said, I want to run Eocene with Fates, or someone else wants to run, I don't know, mid-Holocene, how would you suggest they start? You have all those different levels of from satellite phenology to full. What is the best approach for a postdoc or a grad student?
I would say, you know, I mean, I don't know how useful SP mode would be. I mean, I don't know. I guess that's, you know, what, but I think definitely either the no competition mode, which is we have PFTs and they're kind of growing on their own patches. So we don't have, right now in Fates, like we often have this competitive exclusion problem, like you were seeing with the plots that I was showing in Bonanza Creek. We just had spruce that just completely outcompeted everything else. And so to kind of get around that issue while we're still like fixing the model, you could run in no competition mode. So we would have, each of those PFTs would have its own patch. And so we wouldn't be excluding them in each other. But then you could also do, I would say, like prescribed biogeography mode would be great, where we say, you know, we know that there are these PFTs and they exist in these locations on the globe or in a region. I would say running a point or region scale would be good to start, because for one, Fates is much slower than CLM because it's just we're running, you know, with cohorts and rather than like one PFT. But yeah, and then you'd want to, I would say you'd want to look at get climate data. So I would run in offline mode and just say like, we're going to force it with climate that we know existed during this time, or we, you know, that we're pretty sure existed during this time, and then make your PFTs based on the parameter file, because you can have as many or as few PFTs as you want. Yeah, and I would start there, but I don't know. I'm curious to see hear what Jenny, what her approach would be, because she's probably thought about this more than me. So
I haven't thought too much about Fates. I think my first step would be to find a paleobotanist to work with, just to help me figure out what different parameter values should be, because the number of parameters is a little intimidating.
It is intimidating. Yeah.
I think it would be really cool to try. And yeah, probably offline mode first, just so everything doesn't come crashing down.
Great. Well, we're already dipping into our discussion questions through this discussion. So if no one has, you know, questions directly related to the two invited speaker talks, we can kind of move to the Jamboard with our discussion questions for this session, which perhaps we've already started touching on question 2. You know, how can we start using Fates for paleoclimate research? And okay, I'll say I added these post-its to it just based on our conversation, but if, you know, other people have ideas, feel free to add it to question 2. Question 1 I'll bring up, which is sort of a quite broad question, but I'm interested to hear thoughts, or what are the limitations and challenges of vegetation modeling in CLM for paleoclimate? Does anyone have first thoughts that pop up from that question for their research? Yes, Clay.
Well, I mean, maybe this is just, you know, being stuck a little bit in the past, but a lot of times we're using CLM4, and I found CLM4 is kind of has some interesting maybe biases, and maybe I need to talk with the land group about this. But carbon and nitrogen spin up in times for that, and how much that can really affect things like leaf area index and productivity, and spinning everything up correctly. It can take time, and it's not that well documented. I mean, there's some stuff that I've found online from like CLM3, but it would be nice to have a little bit more documentation about this, and how we could kind of better streamline it for paleo, and also some of the limitations of some of these methods. And of course, always having newer versions and new dynamic features is great. And I'm happy to get on board with those. But, you know, with paleo, sometimes we're a little bit stuck with some of the older configurations.
Yeah, I two of these sticky notes I added just by things that I encountered that I was like not sure what the best approach was. So just I threw them out here in case other people have thought about it. One is the effect of soil composition, and how should we handle that for paleo cases? And then the difficulty of trying, and I know that I've seen some work with other people modeling vegetation climate feedbacks for North Africa during green Sahara period. So it's a universally, I think, hard problem is modeling the coevolution of vegetation and precipitation in regions where they highly depend on each other, and there might be a tipping point in the system between two different stable vegetation climate states. So other than, making the vegetation map you think should exist, and then feeding that into climate to get climate, and then forcing the dynamic vegetation offline with that climate or something like that, some iterative process. It seems to be a tricky problem.
Yeah, I found, even in my work with this other model, it was like, because of the interactions, you could kind of like snowball into these like crazy effects. And it was hard to like, it was kind of, it's like a chicken or the egg. It's like, is it the soil? Is it the precip? Is it the bed? Like they're all interacting. And so it is really hard to like, unless you have it all right at once, you can get really weird interactions.
Right. Yeah. And also like for the high latitudes where the albedo feedback can be important, like I said, my climate was cooler in high latitudes than the one with the fixed vegetation map. And I was like, is the vegetation not growing because it's not cool? Is it too cool because of the vegetation? A chicken and the egg problem.
I'd be interested to hear if anyone else has thoughts on addressing that in their own research. Just curious, just opening that up if other people have thoughts, coming out of this conversation. It is an issue. I am seeing, okay. I just want to make sure on this first question, we've got nice adding post-its, everybody. It looks like we've got a lot of I see one additional post-it, how allocation varies depending on environmental conditions and carbon sink. That's a challenge. Bringing that up. And okay. So we're getting towards the end of our discussion. So I want to make sure that we've touched on question 2. Feel free to add more if you want in post-its. Question 3, which is, what is the best paleo case for testing fates and studying the vegetation feedback? Any thoughts? I see boreal forest and fire interaction, and C4 grass expansion during the late Miocene. Pre-industrial. It's always nice to start where you've got lots of data.
Yeah, at least to isolate the processes. I don't think we had a good grasp on it yet.
I was kind of related to this question. Maybe this is a question for Adriana, which, maybe you don't have an answer for this, but I'm curious, in your mind, does applying fates to a paleo case, even if it's a really simple case, like we don't mess with the modern plant functional types in any way, we're just changing maybe the atmospheric forcing using to force fates. Do you see this as a way to help the development of fates in a way? Can it help that process, or is it something that kind of needs to wait till the modern tuning, the modern evaluation of the model reaches a certain point, and then we can think about expanding the applications?
No, I think, I think it can be like a really cool and useful way to test the model's ability. We're kind of, we can test the model like crazy under current conditions. And then, but that doesn't, paper reviewers are always like, well, like how do you know it's working under future climate? And so I think that's kind of a one way, and it may be something that we do like as like an independent test, but there is the whole problem of we need to potentially make new PFTs. But I think if we don't go back like millennia, we don't have to do that as much, but yeah, like it's a really great exercise to say like, okay, like it's good, you know, from 1940 on, but like, what about like, a few thousand years ago? Yeah, it kind of really gives us confidence in our future projections, and then it kind of can tell us like, oh, okay, we're clearly not getting like this precip interaction right. I think I think it's a totally great process of model development. Yeah.
Great. And then I also just saw that someone added a post-it for question 3, Green Sahara. That's always, yeah, that would be a fun test case. Well, I love our discussion. Technically, it is the break now for the next session. So feel free to, take a break now. Feel free to continue discussion and using the Jamboard. Thank you for attending the vegetation session. And the next session will be the ocean biogeochemical modeling session. Thank you, speakers.
Thanks.
For great talks.
I don't know. Betty has her hand raised.
Oh,
Yeah.
Betty. Okay,
Yeah.
great. Betty, continue.
I thought of two things while we were talking. One related to what we're talking about with fates is my understanding, and Adriana and Bill could correct me if I'm wrong, but the dynamic vegetation code is not going to be maintained as we go forward into CSM3. In fact, it's in CLM5, but it's not supported, may have some. So just to kind of think about that in terms of question 3, and the other thing I wanted to ask Adriana, though, was we know when we've done studies for paleo that soil composition does make a difference. That's been known for quite a while with John Kutzbach and that. Is there a way, how does that work in fates? Can we change the soil, or will it change as the plants do their thing?
Well, I guess so. From what I know about this, so we use the CLM soil decomp routine, and so fates it does have litter fall, but at the patch level, but then we just give all that information to CLM. And so you can specify things like bed depth to bedrock and soil texture based on your surface data file that you're using, and so you could update those. But then beyond that, like if you wanted it to dynamically, like the organic layer depth to dynamically change, that can occur. It's just the spin up on that process is still, with fates, is still something that can take a really long time. And then we're still, even with CLM, I think we're still working on spin up of the soil. So. And then, from my biased perspective, the fire, like connecting the wildfire with that organic layer, I think is really important in the regions that I've done work in. But yeah.
Oh, yes. Yes, Jung-un.
So the difficulties that we've been running into is like how the CSM simulates the climate. For example, like as you saw in Jenny's talk, like tropical land regions are too dry, and that's true for the modern simulation as well. And also like as was mentioned previously, like CSM2 has 2 cold LGM. So I'm curious, like how in developing like CSM3, these issues raised by at least some of them were raised by the paleo group is addressed to the main model development. Is it something that I guess it's probably something that will be considered, but yeah. I'm curious whether CSM3 has different, climate sensitivity and, improved precipitation over land and things like that.
Maybe I can answer the question. So the Paleo group is in close collaboration with the atmosphere modeling group. So I have been participating in their weekly meeting for quite some time now. So I try to bring the Paleo perspective every chance I can. And so we are increasing this communication and the collaboration. And the goal is that for CSM3 to be able to simulate the extreme cold LGM and also the extreme warm early yields. So that's the ultimate goal. And there's a lot of work that need to be done to that end. For example, we need to carefully examine the radiation and carefully examine the moist turbulence scheme, which is proven to be very important for the greenhouse-like climate. So the short answer is that's the goal we are working towards.
And I can add to that the CESM working group chairs and basically anyone interested meet in the development of the model. So they're meeting not weekly right now, but often meeting on CSM3. It still has some development things they're doing just for pre-industrial. So, but once that gets a little closer to being, well, not released, but people are satisfied. The experience with CSM2 when Jean ran the LGM took a little while to prove to them, but they realized that the CSM2 LGM was way, way too cold, even if there's uncertainty in the proxy data. So that message is now accepted that you need to at least test for the LGM, whether we can, during the development, whether we can test for like the Eocene, I don't know, during the development. But yeah, and like Adriana mentioned, there's a lot of interest in using Paleo because we kind of push the model outside its comfort zone and how it's developed. And there's a lot of parameters in these models. So I think I'm not worried because instead of just using Paleo to evaluate the model after the fact, it's now going to be used in the development of the model. So it's exciting, I think.
Thank you.
But I'll just add, I know Jean kind of said this, but we really would love the community to be involved in all of that. So, working with Adriana on fates or working with Jean on things. I mean, because you have the expertise, the interest, and it'll make it a much better model if we get as many people as we can involved in any of these type of things we're talking about: variable resolution, vegetation, isotopes, and soon biogeochemistry.
Yeah, I'll add to that we in TSS we don't have a ton of people hour to go around for testing fates, and so yeah, if you want to use fates, like we would love to have you come work with us, and we have a number of tutorials that can help you get started. And if there are things like getting set up with climate data that you want to use, we have folks that can help do that. But yeah, please email me or Betty can help put us in touch. It'd be great.
Hey, it's 11 a.m. Mountain Time. I think we should move forward to the session 4, Ocean Biogeochemical Modeling. Our first speaker is Josh Cook from the CU Boulder, and he will present us his results on modeling ocean BGC at the KPG boundary. Josh, please take away.
All right, you should be able to hear me and see my slides now.
Yes.
All right, so hi everyone. I'm going to share with you some results as well. There's a lot of struggles from our effort to simulate the climate and ecosystem impacts at the KPG boundary, focusing mostly on the Chicxulub asteroid impact, where we're trying to reconcile our simulated changes to climate and ocean productivity with proxy records. So there are forcings on a couple of different timescales associated with the Chicxulub asteroid impact. First one being the impact winter, operating on approximately a decadal timescale for surface climate impacts, potentially a 100-year timescale for deeper ocean impacts. This is caused by either a soot injection into the upper atmosphere from global wildfires from the impact, with estimates of up to 20,000 teragrams of soot, which is over 100 times the amount used for nuclear winter studies. This blocks sunlight by up to 97%, making photosynthesis pretty difficult. Other aerosol inputs include dust from the impact itself, sulfur emissions from the impact, which become sulfate aerosols when it interacts with water and it's injected into the upper atmosphere. So we're mostly focusing on the ocean ecosystem impacts of this, as well as this longer term warming over the course of thousands of years, occurring from CO2 emissions from the vaporization of rock from the asteroid impact, and warming somewhere around 50 to 300 parts per million from warming from CO2, and that's over the course of many thousands of years. So we're interested in simulating the ecosystem impacts, such as the diminished photosynthesis from reduced sunlight, if that aerosol injection is enough to cause the extinction of phytoplankton. The other thing that's potentially exacerbating that extinction is ocean acidification arising from temperature effects from the global cooling from this soot layer, or from the direct CO2 and sulfur emissions that are occurring. Finally, we're also implementing an ultraviolet radiation damage function in Marble, because all these stratospheric aerosols are having negative effects on the amount of stratospheric ozone, potentially letting in a lot of UV radiation at the surface. So once the aerosols clear around 10 years post-impact, that could be having an effect on the ocean ecosystems as well as land ecosystems. Mostly the focus of this talk is trying to get that equilibrium biogeochemical ocean state though. So we have it has to equilibrate with high CO2, different solar constant, and the presumed paleogeography of the time, which is the major challenge that I'll be talking about today. So a bit about our model setup. We're using CSM 2.1.3 with CAM4, WACM4 for the spin-off simulation. We're using WACM4 for the actual impact simulations with their interactive aerosols, tropospheric stratospheric chemistry. For the ocean, we're using Marble, POP2. We're using two different resolutions, a 3 degree for the really long-term simulation. So if we're going to look at the effect of CO2 over the course of 50,000 years, and we're using the higher resolution for the impact studies over the course of 50 years. Our Marble we have 4 phytoplankton, 1 zooplankton functional type. So we have small phytoplankton, diatoms, diazotrophs, and coccolithophores, and we're interested in the coccolithophores, which potentially went extinct at the boundary. So we're trying to see what the mechanisms for that, for their death is essentially at that boundary. And finally, we have carbon isotopes enabled to help us reconcile our model simulations with the proxy records. These are some of the boundary conditions we're using. So CO2 is 850 parts per million. Methane is pretty high, around 2,400 parts per billion. Average global sea surface temperatures are in the range of 25 to 26 degrees Celsius. In our model, solar constant's a bit lower than present day, 1353. And we've created all of our initial conditions for this late Cretaceous period, just global average profiles of present day, and let the model spin things up. But the physical ocean state is starting from a spun up non-BGC case that's been spun up for around 3,400 years and is pretty much at physical equilibrium. The thing that needs to be configured for paleoclimate as well is all of these biogeochemical nutrient forcing files. So we also employed some pretty crude metrics here. For example, this is showing total sediment flux, iron flux from these sediments. So for example, in the new paleogeography on the left, there's these very shallow seas have higher sediment flux because the same vertical levels in the present day have iron flux. That's pretty high. But we've made so the global integral of sediment flux in the late Cretaceous is scaled to match the pre-industrial. And we do the same thing for iron flux from thermal vents. So in the new paleogeography, there's this broad emission of iron flux along these mid-ocean ridges that somewhat match the how it happens in the pre-industrial as well. And we have river flux set up so that it's basically just around the continents and scaled to match the present day or the pre-industrial as well. All of these nutrient flux forcings, we did some sensitivity tests, and they don't seem to be, net primary productivity is not super sensitive to these, but they are very sensitive to the aerosol deposition and the iron flux the derived iron flux that comes about from the aerosol deposition. So we generated some aerosol deposition files using CAM4 and a bulk aerosol module, initially resulting in a very large amount of iron being deposited from the oceans or being deposited into the oceans. So this is the spatial distribution of iron flux derived from aerosols in the new paleogeography compared to the pre-industrial. And in some simulations where we modified and scaled the amount of iron flux, we found just the aerosol deposition files that were created using the aerosol module led to like 60 to 70 petagrams of carbon per year. So we scaled that down a bit to match the present day, meaning we had to change the ratio of fine to coarse dust in the forcing file, brought it down a bit. And so this is the new forcing that we're using for aerosols and dust deposition. And we don't really know what dust deposition was like in the Cretaceous, but this is bounding it with present day or pre-industrial conditions this is our best guess of the nutrient flux forcings. So before we actually spun up the late Cretaceous, we performed some initial tests to get a sense of how marble responds to the forcing that we're going to use, so reduced sunlight in this case. By here, we just reduced photosynthetically active radiation, or PAR, to 10% of actual values. We also tested out the sensitivity of MPP to these loss threshold parameters that are in marble, which is this minimum biomass parameter for phytoplankton and zooplankton. So we ran this test where this loss threshold was set to 0, allowing for essentially the extinction of phytoplankton and zooplankton. And then in a final test, we left this parameter unchanged only for zooplankton, which essentially allowed for more grazing. So this top panel is the total net primary productivity in the oceans. The PAR reduction is right here. So it's an instantaneous NPP effect. This black line that's kind of behind this legend is the control run. So a sudden reduction in productivity and a lot of sensitivity to these loss threshold parameters. So when zooplankton are allowed to tend to 0, phytoplankton perform slightly better, but when these are unchanged for zooplankton, phytoplankton perform worse. The main result here is this big spike that's controlled, seems to be controlled by the amount of productivity that's occurring during this time period. At the time we set PAR back to normal, it uses up nutrients that weren't being used up during this time of low sunlight. And there was another paper recently that found a similar result. Even in the simulation, they put in a lot of dust, supplying a lot of nutrients to the ocean. So we're able to get that response even without supplying extra nutrients into the ocean. So this seems to be a consistent, even in a different biogeochemical model, that after sunlight returns, you get this big spike. Now on to the, we also looked at coccolithophores. So that's the added functional type that we are looking at. And it is extremely sensitive to these tunable parameters. When it is allowed to tend to 0, it seems to have an advantage over other functional types. But when you allow grazing, that's not the case. And then post-impact, it seems to it has this much higher state after the fact. So this is an interesting result. And once we have a fully spun up ocean, we will do all of this again and see if we get the same things. But onto the actual spin up itself, which is the main thing that I was going to talk about today. Our initial O2 state from pre-industrial, likely a little higher than it should have been. And over the course of 2000 years, we lost 30% of all oxygen in our oceans. Seems like a lot. It seems to be tending towards equilibrium at the end. And it seems to be controlled by a ridge in the Pacific. So this is an animated plot of actual O2 values at 3,800 feet or 3,800 meters depth through time in our spin up. And you could see this really low oxygen water just being pooled in by all of these ridges here. And it's leading to areas of basically oxygen minimum zones. So as a result of that, we're getting global denitrification that is kind of running away. So 50% of all nitrate has been depleted because of this low oxygen zone in our spin up. So the solution that we thought of to try to fix this was to put trenches in. So these are ideal age plots showing that there's older water here. And when you put in these trenches, it gets a little younger. So the idea is you put in these trenches and you encourage deeper water flow into the Pacific, possibly minimizing these oxygen minimum zones and stopping the denitrification in the late Cretaceous. And so we ran these simulations with the trench case, and oxygen is still declining. So even though the flow is young, the waters are younger in these areas, it's still being depleted. But nitrate is not being depleted as fast. So we've seemed to have minimized the oxygen minimum zones, yet have not been able to get oxygen to stop declining, which is an issue in the present day as well with marble. So it's kind of an issue we knew we were going to deal with. We're still kind of looking for solutions to fix this. We were really hoping that these trenches would not fix our problems, so make things a bit better. So I was hoping for better results on this slide, but that not the case. And that's essentially what I have to report of our struggles here. We're still going to run this trench case out to see if the reinvigorated deep flow will keep those oxygen minimum zones as small as possible and stop this runaway denitrification, so we can have this equilibrium biogeochemical state. But if not, we'll probably resort to the ad hoc fixes that were used in the present day to just stop O2 from being consumed as quickly. And that's basically what the presentation.
Okay, thank you. And we have time for questions. Anyone? Maybe I can ask a quick question about the oxygen problem you mentioned. So you are running the model in a very unique configuration. So CAM4 physics and the cost resolution. I'm wondering if you use the configuration to do the industrial present day, climate simulation, can you sort of tease out the bias, whether it is from physical climate or is from biology or chemical processes?
I don't, yeah, in present day, I'm not really sure where the bias comes from. But it seems like physically, we've been able to get the ocean to be less sluggish. My sense is that it is a biogeochemical effect. But we're still looking into ways to diagnose that.
Okay, in the interest of time, maybe we move on to the next presentation from Keith Lindsay. Keith is a scientist at NCAR, and he will give a presentation on the update of Ocean BGC and the fast spin-up method in CSM. Keith, please start.
Thank you. Is that coming through?
Yeah, looks good.
Okay. I'm going to give a brief update on the status of Ocean BGC and fast spin up for CESM3. I decided to, I'm targeting what I think might be of interest, particularly to the Paleoclimate Working Group, but I'm going for brevity so that if I'm missing things, there's more time for questions because of things that I didn't think that you're interested in that you might be interested in. In order to talk about what's going on in CESM3, here's a brief overview of Ocean BGC and CESM2 for comparison purposes. In CESM2, we switched to using this library called MARBLE, which stands for the Marine Biogeochemistry Library. Josh spoke about that briefly. He mentioned it. The key feature about MARBLE is that the computational scientific core is independent of the GCM. And the reason that we switched from an older version of the Ocean BGC to MARBLE is that we knew we would be switching away from the POP Ocean model after CESM2. So we developed MARBLE to aid in that transition. The main scientific features of MARBLE are it has the typical nutrients, phosphate, nitrate, ammonium, and silicate are the macronutrients, and iron is the minor nutrient. The plankton structure in MARBLE is configurable. In CESM2, the configuration was what we call 3.5 autotrophs. We had diatrophs, diatoms, nitrogen fixers, small phytoplankton, and an implicit calcifying pool. Implicit in the sense that it was a fixed, well, it's a variable fraction of the small phytoplankton as opposed to a full implementation of that functional group. And we had one grazing group in that configuration. I think of particular interest to the Paleoclimate Working Group is the nature of the fluxes and the forcings for the model. And this is something that Josh alluded to with his work. We have prescribed forcings of riverine inputs, atmospheric nitrogen deposition, and sediment iron fluxes. So if you're doing experiments that have a different climate regime, like LGM or different continental locations, these are forcings that would need to be recreated. That we have these provided for 1850 conditions and historical and future SSPs. This would be effort to generate these for other configurations. There are, compared to CESM1, the atmospheric dust and iron deposition is now prognostic coming from the atmosphere. We have a parameterization, we get dust directly from the atmosphere. And so that there's no additional work needed to get that forcing going in different configurations of CESM. And the iron is based upon the atmospheric provided dust and black carbon. Marble has support for carbon isotopes biotically. This is based on previous work of Alex John. By default, these biotic carbon isotopes are turned off, because they do add considerably to the computational expense of the model. And there's an abiotic radiocarbon that is included in CESM2 in POP, which is separate from the Marble library. Marble only simulates biotic tracers. So that's the background with what's in CESM2. Transitioning to CESM3, that the big thing going on is that, I'm sure you've heard, we're changing the ocean GCM from POP to MOM6. MOM6 has more modern computational techniques, uses more advanced advection schemes, has a time varying vertical coordinate, can handle natural freshwater boundary conditions. So you can do studies of sea level rise, for instance. There are a number of scientific reasons why we're doing this transition away from POP, and MOM6 was what we decided to use. So with the transition to Marble and CESM2, the main thing that we need to do then to switch Marble from coupling Marble from POP to MOM is writing a driver layer. That is nearly complete. A driver layer for MOM6. Sorry, I wasn't complete there. That is nearly complete. There are some couplings between Marble and the rest of the system, like using chlorophyll to compute shortwave absorption in the ocean, and passing CO2 fluxes back to the flux coupler for use in coupled carbon climate simulations that are still underway. I think maybe the most substantial remaining action item is that when Marble was developed, we were using POP, which is a CGS, uses CGS units, and all of the Marble input and output is hardwired to be CGS. We weren't forward thinking enough to do that flexibly. MOM, however, uses MKS for its units. And so right now, when we do this coupling simulations with MOM with Marble, we do get CGS output of Marble variables, which is, I think, undesirable. And we haven't really quite mapped out how what we're going to do for a CGS to MKS transition, what we're going to do, but I think that might be one of the most substantial remaining to do items. We are coupled to Marble, except for these gaps. We do have Marble running with MOM6. We've been doing several ocean ice experiments with this configuration and comparing the simulations to companion experiments that were performed with POP and Marble, and the simulations look qualitatively similar. In the GCM simulate different physical simulations, so we don't expect to see identical behavior in the ocean BGC, but we do see general similar behavior. So that's sort of the coupling of Marble to MOM. Some additional aspects that are relevant, that are worth mentioning, is that the likely plankton configuration for CESM3 is we're moving to a full 4 autotrophs, where the calcifiers are now an explicit functional group instead of being a fraction of the small phytoplankton. It's fully prognostic calcifiers, and the calcification depends upon the carbonate state of the ocean. And we've moved to 2 grazers. We've been doing some simulations with Marble with a high resolution 10th degree eddy resolving ocean model, and found that having 2 grazers leads to a cleaner, well, when we run with the 1 grazer model in the eddy resolving model, we get an unrealistic distribution of functional types in the out of Marble. in using 2 grazers seems to be more stable with respect to model resolution. This is not something we fully understand why that's the case, but having multiple grazers also enables marble to be better suited for other scientific goals. For instance, coupling to fish models, which is another side project that's going on that I wasn't really going to go into detail about the coupling to the fish model. If someone wants to know more about that, I can describe that in the Q&A. There's also a higher complexity configuration that's under development with collaborators at the University of California at Irvine, looking at 8 autotroph 4 grazers. Some other points of note are that the abiotic radiocarbon has not been implemented yet in MOM6. So when we, as I mentioned in the previous slide, that's separate from marble. So when we coupled marble to MOM, that did not give us the abiotic radiocarbon sort of for free. That has to be implemented separately. That is a remaining task to be done for CESM3. There was some conversation in the session earlier about water isotopes, and I'm just mentioning that as a question mark because we do not have water isotopes implemented in MOM6. I think the science of water isotopes in the ocean model is not overly complicated, but there's still work to be done to implement that. Another sort of scientific feature that has been discussed repeatedly over many years is the coupling of ocean BGC to sea ice BGC. There is some support for biogeochemistry in the sea ice model of CESM. The coupling of the sea ice BGC and the ocean BGC is desirable, but I'm not sure if that's reasonable to think that we're going to have that in place for CESM3 just because of not having adequate resources to implement it and evaluate that it is working appropriately. If there are people that want to work on that, we'd love to coordinate activities with you. So that's sort of a very high level presentation of ocean BGC status for CESM3. Regarding spin up of ocean BGC, a Newton-Krylov solver was used in CESM2 to spin up ideal age, abiotic 14C, DOM tracers, and DIC alkalinity tracers. This is work that I've working on this Newton-Krylov solver. That's a research project of mine. And we were able to spin up some aspects of that for the pre-industrial CESM2 runs using a development version of the Newton-Krylov solver. This is not all BGC tracers. It's not yet in production mode, ready to handle nutrients or oxygen or iron in the ocean BGC. There's a simple, the Newton-Krylov solver has been extended to work on single macronutrients in a 2D model that the Newton-Krylov solver can be applied to. You don't have to run the solver just on the full GCM of CESM3. You can apply the solver to other sorts of models. So that's some of the extension work that has gone on with the solver beyond what was done, how it was applied for the CESM2 spin-ups. Some ongoing Newton-Krylov development research projects are handling the time-varying vertical coordinate of MOM6. This makes it, having the vertical coordinate in MOM6 vary in time is great from a point of view of simulating water masses more accurately and eliminating spurious vertical diffusion. So in the interior of the ocean, for instance, you can have more of a adiabatic coordinate system. And so you get a better simulation of water masses, but it does complicate some diagnostic analysis of the model. For instance, just in the Newton-Krylov solver, just taking an end state of a run minus the beginning state, when those are on different vertical coordinates, there's some complexity there already. And how that extends into the rest of the solver there's a lot of details to that. With it as a ongoing research project, I think it's a high priority for CESM3 to push this through. Also, research projects are handling multiple macronutrients. Some of the work of handling single macronutrients will need to be extended to the way that we handle multiple nutrient limitations in marble, and also extending it to oxygen and iron that have more complicated source sink terms, and eventually temperature and salinity. That is probably more aspirational for CESM3.
2 minutes.
And that's it. So we've got more time for questions.
Okay, great. Yeah, thank you for the very nice update and a lot of useful information. So does anyone have a question? Betty, please go ahead.
Okay, just maybe I missed it, Keith. In marble in MOM, are you going to have the C13 biotic?
Oh, that would be that's part of marble. That is part of marble, and so it's
Okay,
it's available when just coupling marble to a different GCM. You get that for free, but by default it will be turned off. Yeah, it's this. We still have the same prescribed forcings, prognostic forcings, and support for carbon isotopes in marble. All of that has carried through to MOM, well, independent of the GCM.
Okay, there's a few questions in the chat. So Paul asked, is there any chance BGC can be configured with CAM5? Maybe it's a question for Keith.
I'm not quite sure what that means.
Okay, so I think for writing,
maybe they could do they want to be more specific about what they have in mind?
Paul, do you want to unmute?
Yeah, so it seems like most of the community, the paleo community, is running BGC with CAM4. So there's now a lot of paleo simulations out there that's just normal CAM5, but then we're having a problem with configuring it with the BGC. So yeah, just a general question.
I think the only way that I can think of that the ocean BGC has a dependency on the version of the atmospheric model is that we're getting the ability to get a black carbon flux from the atmosphere so that we can get the iron deposition. And all of our in CESM2 we were using CAM5. I don't know if that's available. I don't know that if CAM4 supports the simulation of black carbon flux. It might actually be harder to say, can we do simulations with ocean BGC and marble with CAM4? But I think we're doing CAM5 already. I think that's what was in CESM2.
Great, thank you.
Sure.
Okay, another question in the chat. Will any of the fast spin up method developments will be backwards compatible?
It might be necessary to back. So it depends upon how far back you want to go and how much effort it would take. If you were trying to do something before, the challenge is that the Newton-Krylov solver requires additional diagnostic output from the ocean model so that it can compute the increments as it's doing in its iterative solve. And those additional diagnostic outputs are being ported into Marble. If you're talking about a version of CESM that predates the inclusion of Marble, that would require more effort to get the diagnostics needed for the solver into that older version of the Ocean BGC. I think if you're just porting the diagnostics, if you're talking about a version that includes Marble but doesn't have these additional diagnostics, I think that would be a lower bar to backport the solver to that configuration of CESM, but I think it would be a higher bar if the version of CESM was not running with Marble. Does that answer your question, Clay?
Yeah, sorry, they're just doing construction next door, so I couldn't talk for a second. But yeah, I was just mainly thinking for using POP instead of MOM, if these new features would still work with Marble configuration like CESM2 setup.
Yeah, I think it would be this. Yeah, if you're talking about that, I think it would be sort of like this. I think there might be some effort to backport the diagnostics that the solver is going to be depending upon. But I don't think that's insurmountable. And someone who's savvy like you are would be able to do it.
I'm not so sure about that. All right, thanks.
Okay, do we have more questions for both speakers, Josh and Keith? If not, we can move on to the discussion session. We have a few questions here. So we can take a look. Okay, let's start with the three questions we have here. The first question, what are the major roadblocks for paleo application of BGC and the fast spin up? I think both speakers have touched upon this question. For example, the spin up was mentioned, the boundary condition requirement is also mentioned. And also, if you have a bias in the simulation, how do you diagnose whether this is in a physical climate or ocean BGC, and how to improve upon from the available results? So do people have any more thoughts on this? You could either unmute or put some text in the Jamboard. Maybe I can ask a question to Keith. You mentioned that currently people at the ocean modeling working group, including the biogeochemical modeling working group, are doing some high resolution simulation with the BGC capability. So of course it will be very expensive to do. I'm wondering how different are the solution you get from the high resolution. So is that something we want to consider in the paleo context?
That's a great question. I have not been involved personally. I've only been involved at a cursory level with that project. So I'm not really prepared to describe the differences in the simulations. I'm not so familiar with the qualitative behavior of the high-res BGC simulations.
Okay, that's fine. If we don't have further comments, maybe we can move on to question number 2. How can we develop and improve ocean BGC related model capabilities, and what are the required resources?
Kind of think one thing that ties in with some of the other stuff is maintaining a lower resolution model that we can work with for paleo, because the spin-up procedure can take a long time. And what I think we're finding is that even with the 1 degree case, which I mean is probably okay, maybe going forward, it gets quite expensive with the BGC. And so spinning these things up for really long periods of time becomes prohibitive. So I don't know what the ocean plans are going forward, if it's going to maintain 1 degree, or if they're planning to go to a standard higher resolution, but I think would be really helpful and necessary for the paleo community.
Keith, please.
That's a great point, Clay. The target configuration for MOM6 and CESM3 for our sort of workhorse version is around 2/3 degree. And MOM is a bit more expensive per degree of freedom than POP because of the more sophisticated numerics and the time varying adaptive vertical coordinate. So MOM is more expensive than POP for these higher res, because we're targeting a slightly higher resolution, and it's more expensive per degree of freedom. I've heard some talk about trying to support a 2 degree version of the model. I'm not familiar with, I think the challenge there is personnel to work on that. The configuration of the workflow to generate the grids for the 2/3 has been for MOM. Gustavo Marquez has been working tremendously on making that a well-documented workflow. And so I think that will help in the creation of a lower res version of the ocean model. But I would think there might be considerable effort to tune it to get acceptable simulations from, including parameter values, mixing parameter values, as well as bathymetric tuning, so that you get appropriate resolutions in key flow points in the deep ocean.
Good, thanks.
Thank you, Keith. Betty, do you have a comment?
Yeah, we did hear an interesting talk at I think it was the Ocean Model Working Group meeting, where a researcher in Potsdam was trying to work with a 3 degree version of MOM, and it didn't work well. But there did seem to be the consensus, and there was a lot of GFDL people at this Ocean Model Working Group, that a 2 degree, they've done a little bit with a 2 degree, looks like maybe a viable resolution to try for a low resolution ocean for MOM6. I don't know, and maybe Keith knows, talking to Gustavo or Alper, is it going to be hard to create different paleogeographies in MOM, with MOM or CSM3?
I know Gustavo has been working on making the workflow well documented. I I have not looked at it myself to know how hard it would be to, so I don't know how hard it would be to apply it to a configuration where you have, for instance, some different continent locations. So I think the goal is to make it more flexible and documented so that one can follow the steps. But I don't know in practice how complicated that is when you've got different landmass configurations. That's a good question.
Okay, in the interest of time, maybe we move on to the third question. So what time period science question would be a best starting point for starting to look at the BGC capability and the related science question? So it's sort of related to question related to Josh's work and Clay. So I'm wondering whether the KPG is, of course, a very fantastic question to investigate. I'm wondering, do you have any thoughts on the other time period that might be like a smaller step than the KPG, which is very different from the present day climate in many aspects? Betty?
So I don't want to pick on one of our participants, though I can see them all, and hopefully he's online still. I was thinking of the Pliocene, because it's a little bit closer, it's not quite as extreme. But I don't know enough about the records. So Harry, are you there, Dowsett? What do you think about Pliocene for this? Oh, maybe. Yeah.
I only just ran back in, so I heard my name. I'm sorry.
Oh, well, we're thinking
I missed the
about what
question.
what time period science question would be a best starting point when you think about using ocean biogeochemistry, all the different types of, I'll call them bugs for now, and also having things like carbon-13, carbon-14. Seems to me a lot of your records might be based on that, so it'd be an interesting time period to look at with these features.
Yeah, I mean, it's always sort of well, in my opinion, like a sweet spot. We do have a lot, not as much as you would have, looking at last interglacial, but a lot more than anything deeper than that. So.
Yeah, I was thinking in the whole debate on the PMOC and, whether there was a Pacific Meridian and some of the records for that. So, okay. And it's easier probably than the KPG, as you said.
I'll stick close by now. Sorry.
Oh, okay.
Another thing I want to add here is that in the current paleoclimate simulations, some of them actually included ocean BGC. Please correct me if I'm wrong, Betty or Esther. For example, the Holocene, maybe also the last interglacial. I think we can do a better job in letting the community know that we do have some isotope enabled, BGC enabled simulation. So you can start to examine this simulation if you are interested in the time period. Okay, it's 11:50. Unless there's question or comments from anyone, let's take a break. It's been a long morning, but please stay around, and we have a final special session next. sharing and organizing the paleoclimate working group and the community resources from Esther. So we see you at 12 p.m. Mountain Time. Hey, it's 12 p.m. Mountain Time now. Let's get started to the special session on better organizing and sharing of working group and community resources. And Esther will give us a presentation on this. And Esther has been a member for the Paleoclimate Working Group for a very long time. And she recently retired. But we are really fortunate to have her coming back, work as a casual to help the working group to organize the available resources. Esther has made a great contribution to the working group, including leading the development of isotope-enabled CSM1 and serving as the co-chair of the working group. And she has been a great mentor for many early career scientists, including myself. So Esther, please start sharing your screen.
Thanks, John. That was really kind introduction for me. Yeah, thank you. Today, I'm going to present some recent work that we've been doing to update and retune our Paleoclimate Working Group webpage to make it a place where there can be greater and more improved engagement with the community. So one hope for our pages is that it's a place that we can highlight the CESM paleoclimate simulations that are done both at NCAR and also out in the community as well. So it can be a place where you can highlight your work once you feel ready to do that. Also, we would also like to be able to have a catalog of resources that the community can use in constructing simulations and doing all that, creating setup tools and contributing those to our webpage as well. So I think what I'll do is take you straight to our page. So I'm going to share my screen. Find it here. Okay. All right. There we go. So this is the main CESM webpage, and to get to our working group pages, you can tab down to our working group here, and then you're here at our top level page. The first blurb is just some information about our working group, what it's all about, what kind of activities in a general sense that we do. And then if scrolling down, and you guys can see this, right? Good. Okay. Scrolling down the page, there are different sections. First are a list of links to simulations, starting with recent and notable simulations. These are simulations that we get asked about a lot. And one that I just added from Sophia, because she had a paper that was published in 2022 for the Pennsylvanian, was just recently added. This work was done at the University of Michigan with Chris Polson, now at University of Oregon. And I'm just highlighting this as an example of how the community can be presented on our webpage. And then we have simulations that are organized by CESM versions. So if you're looking for simulations for CESM1, you can click on this link here. And then we also have them listed by time period. And we have simulations for all time periods except for the Miocene and the Eocene, which we know is a very active area of CESM research. So we hope that we can bring in some of the work that the community is doing in these intervals when those scientists feel ready to highlight here on our page. And then we have paleoclimate resources, which I'll get into a little bit later. And then finally, information on how to contact our co-chairs. And then over on the right are just some links to these particular pages that go off in these different directions. First, we'll look at the page for the simulation by model version, and here they're all listed. All the simulations that we have currently in this catalog are listed here, and some that we have planned, like Jean's paleo-calibrated CESM2 LGM simulation that he's done. Okay, and then going back to the simulations by time period, I can show you kind of what a simulation page would look like. If we go down to the last interglacial, one of the recent runs is the CESM2 with the active evolving coupled ice sheet model SISM2 for the last interglacial is shown here. And this is the page that would exist for a particular project or simulation. So there's a blurb that explains a little bit of description about the simulation. There are some links to some data sets and also a reference to a paper where further details can be found. And then some verbiage about terms of usage for the data. So each scientist can craft their own terms of usage. And then some project details where we list simulation names and model version and resolution and other things like that. And then how to find the data and acquire it. This particular simulation is on NCAR's Climate Data Gateway, which is a bit slow to get to. There we go. So, and here's where you can actually download data from this simulation. We don't have all of our NCAR simulations yet on the Climate Data Gateway right now. To get some of our simulations, you would have to ask us and have access to our Glade campaign store, but we hope to eventually get all of our simulations that we have on campaign accessible through the Climate Data Gateway, and then it's very easy to download data that way. We can't really host at the moment community simulations, but we can make up a page like this with information about how someone interested can acquire data from the particular community member. And then finally, there's a link to diagnostics if they exist. Okay. Moving on to resources. And this page is definitely a work in progress. It's part what we had before, and it needs some more updating. But it starts with sort of a jump menu here that you can use to jump down the page. And then you can find CSL proposals and read about what has been proposed to be run as working group simulation through the Climate Simulation Lab. It doesn't have the latest one on, but when GoCon posts it, we can add it to this list here. And then the one I'd like to highlight the most is a place for user contributed code. And this is where we could list if people have public GitHub repositories towards tools that they may have developed. We can list them here as people start using more and more Jupyter notebooks and things like that, we can link to those particular tools here on this list. For example, and these go to a GitHub repository that we have for the Paleoclimate group, where you can download some tools. This one is for the topography. I think it's a topography updater for using SISM. And then down here, there's if we've developed a particular comp set, this is for like the PETM work that Christine Shields was involved in, then this gives you name lists for the comp set. Okay. I think I've covered that. I want to share. Nope. Gosh. Yes, this. Okay. Down to here. I want to encourage the community, external community, to contribute your simulations and tools to this catalog. It helps to promote the working group activities. It enhances collaborations with a wider group of researchers. It helps to reduce duplication of effort in developing some of these tools, and also maybe with you know, creating ensembles of simulations, or there's lots of ways that collaboration and reduction of duplication of effort can be done if we have one place to sort of gather our collaboration. Also, this is a way that we found output is really easily shared with other interested researchers, especially those who don't have computer resources or expertise to run CESM, in particular graduate students, early career scientists that may be starting out and wanting to get started in using CESM, but also the data community has been a big user of some of our simulations, such as Trace, to compare to their proxy data products and their reconstructions. So I think, yeah. So how would you contribute your simulation or your tool to the Paleoclimate Working Group catalog? First, contact the working group co-chairs, and they can give you a template, and almost all of our simulations keep to the same sort of template like the one that I showed, with really what you give back in terms of like a title, a description of your project or experiments, any references that you would like to highlight, point people to, and also a acknowledgement policy for your work, and then project details, and then how and where you can acquire the data. And so, you know, contact information, DOIs, and then terms of usage, how you would like, if you would like any terms for how your work is used, and then any diagnostics if you have links. Just one more final thought I had is just thinking about best practices for sharing simulations. And that is to post-process your history time slice output into single variable formatted time series. And this isn't the standard way that when you run CSM, you get output. Usually they're in time slice chunks, monthly, daily, whatever, hourly. And what this is good for. It compresses your file sizes, particularly for the ocean. And also it helps in reducing the amount of data that one would need to download from a repository of data, because you only would be then downloading the fields that you're really interested in. And then later, as the simulations become, more aged in their use, you can reduce the number of fields that you're storing, so that reduces your storage, which is a very big consideration in hosting using CESM data and keeping it stored. And there's a link to where you can find information about this post-processing of output from CESM runs. And that's what I have. Can take any questions if anyone has any. I see hands raised. Jean?
Oh, it's clapping. Thank you,
Oh,
Esther.
it's
really...
clapping. Okay. I guess I turn it over to you now.
Okay.
Is that?
Yeah, thank you. I think it's really exciting to see that we have centralized place to have all those valuable resources to the paleoclimate working group. Okay, for the audience, do you have questions for Esther, or do you have any suggestions? Betty, please.
I was just going to add to what Esther said in terms of why you should do it. Hopefully they get lots of citations, because people will see your simulations, see your papers. So it helps with the citations to make people familiar, which for the early career I know would be great.
Clay I see Clay's hand next.
Thanks, Esther. Yeah, I guess this is kind of a general question, and thinking about getting more resources for something like this, which I think is really great. It seemed like you couldn't really, you don't really have the resources to store a lot of community data at the moment. But for instance, if we were to write a proposal or something like that, is there a way we could integrate with this and say, hey, we're putting in money in order to support our simulations being available through this resource or something like that? There's been any consideration of that, or if that might even be something that's feasible at all?
I think I think Betty might have a better answer for you about that. I think it's kind of above my level in terms of whether money can be given to NCAR to support larger storage capabilities. We did hear that we can host data on our own working group campaign store if there's a close collaboration or they are a working group co-chair, for example. But right now we are probably one of the largest users of campaign space. We have a lot of simulations that we just moved from our tape archive system, the HPSS that was being retired, and we put those on our campaign space, and we have hundreds of terabytes of data. And we would have to, I think one thing we should make is some kind of plan or policy about which fields to save. Maybe in a tiered system, like the most important fields to save are these, please keep for forever. And then tier 2 is nice to have. People have used them in publications. And then tier 3, nobody's downloaded these and they're not that useful, but maybe we can age them off the system. But right now we don't have that. We basically save a lot of fields and then turn those into single variable formatted time series. And it makes for very large data sets. But I think community voices towards this is always welcome for MCAR. I mean, we have a small group, and so and we jostle for campaign space with other working groups. So hearing from the community that storing of these valuable simulations, it would be really great to have. So.
Hey, Ryan.
Yeah, I think this might be a question, or maybe I'm just behind technology. So is it possible to create like a guest Globus for our for somebody who wants to download data? Because I know, well, I've been asked by people for data, and especially the ocean data, it's hard to, it's slow if you just download through the web link. And for our the climate simulations hosted at University of Leeds, they created the guest Globus access for people, so that made it much easier.
Yeah, there is that ability that I read about recently, looking through all the pages about campaign and Globus. We haven't done that in the past. I don't know, maybe John has done that, but there is a way to do that. However, I hope, Gary says that we submit our simulations through something called GDEX, Geophysical Data Exchange, or something like that, an NCAR sizzle project. And Gary gets the information, and then they work on creating the Climate Data Gateway links and processes that are needed to be able to download directly from the Climate Data Gateway. So I think, we'll be submitting that for all the simulations that we don't currently have on the Climate Data Gateway. And then as for the community, I think there are ways to make guest access on Globus. Let's see if I can find it.
Yeah, I would like to try that.
Jun, next.
Well, thank you. Thank you for all your effort. Is there like, any effort, or is it already shared? So the input data file and the name list, because probably the most difficult thing when we are moving into the paleoclimate is, getting the right topography, bathymetry, and things like that. And just contacting co-chairs. I mean, it's difficult for everyone, but especially for early career students, that's actually a very, very difficult barrier. I mean, if I ask my students to contact one of the co-chairs, I don't think they would ever contact, the co-chairs. Maybe some people, but I'm just, using an example. But so I'm curious whether there can be a way, for you to share input data and the name list file.
I mean, we do have some, like for the deep time recipes section, there are some recipes for how to create input data on our resource page. at the currently, I think that's a good idea. Yeah, it would be up to the individual researchers to allow the sharing of their input data. And we hope that, you know, by having a catalog of simulations with contact information for the lead investigators, that would be a way of contacting them. I mean, I don't know how to like encourage graduate students to reach out, you know, but I think that's an important skill probably to begin to have. Yeah, I mean, a catalog of input data is kind of hard because a lot of it is very specific to a particular model version or a particular resolution. And yeah, I think certain amount of reaching out is probably going to be necessary at some level to work, and it just helps with collaboration that way. And just knowing what other groups are doing is, we hope helps in the engagement here. If we can gather together in sort of a catalog way what other groups are doing for different time periods, then we you know, we can kind of help that process a little bit. So.
Okay,
Thank you.
Sophia, and then Patty.
I have two comments, which the first one was just back to the Globus question about being able to create a public account on there. I think this would translate. When I've shared simulation data with people who don't have an account on Glade or on, you know, on Cheyenne, I found Globus was the easiest way to do it. I would create another directory on Globus that had access if you had a link to that. And I was able to send a link to people, and then they had access to the data in that Globus directory. So yeah. I'm not sure if that was contingent on their institution having access with Globus. I don't, but with the two people I did this with, it worked really well. So I think it's possible.
Yeah, and that's the guest collection route on Globus. And Gary Strand, who's kind of our data lead in CGD, he told us that that's best for really time-limited transfers of information and data sets and things like that, but not more permanent ones like what we have through the Climate Data Gateway. So, but yeah, you can do that. Yeah. But again, you have to start by reaching out first and finding people that might have what you're interested in. And yeah.
And then I just wanted to add one additional comment on the idea of sharing the nameless settings and the input files for these, because I was thinking about that. Of course, it would be nice, even on the Paleoclimate Working Group website, to give people the option to, you know, if they're supplying you with their already published simulations, maybe they can give you some information about their nameless on that same page. But at the same time, then I'm thinking about, like, for deep time, like for my Pennsylvanian simulations, creating those boundary conditions was a multidisciplinary effort where maybe that person wasn't an author on my paper, but for sure I had specific sort of citations of their papers that were included in my paper to make sure they were credited for like the process that they put in and the knowledge they put in to create the boundary condition. So I would worry if that information was all just public without any sort of stop to say, oh, I know who's using it, or to be able to put my input into it. I would worry that person wouldn't know, oh, cite these papers, credit that effort, as was done in my papers, if that makes sense. So I would like that person to reach out to me, even if I did give them all that information, to know, just so you know, this paleobotanist helped me with the vegetation, and this geologist helped me with the topography, you know, just the list goes on. Yeah, that's my comment on that.
Betty?
Good point.
Yeah, I don't, related to that, and this is just starting, so I don't know all the details, but NCAR is starting to do things like containers. And I get the feeling that the container would include not only, this is the code and all its stuff you need, but it would have all the name lists and the forcing files and all that. It's something I guess we could look into, because it seems like if, I don't know how that would work for everyone's simulations, but at least if we're doing a simulation at NCAR, maybe we can try doing these containers, because I think the idea is you can even port it to your own machine. And do you know more about containers, Sean?
No.
No, okay, but
Sorry.
I think it is a way to maybe, like Shen Yun wants, for a grad student to be able to grab that and try running. Of course, one advantage of having this website with all these is hopefully grad students could run a different simulation, a sensitivity off it, where they change the CO2 or something where they don't have to run a full one. They can start from something that's already there and make some changes.
Jesse?
Well, there's Jesse. He probably knows containers.
Sorry, yeah, I was just gonna jump in. My understanding of containers is it gives you the source code in the run environment, so you can run the model without worrying about compilers and all that. But my understanding is you still need some sort of server to provide the actual boundary conditions and initial condition files, which I think can come through Globus or Subversion or FTP or whatever. But yeah, it's just so I think it helps. Containers help run, but I think you still need that source of here is the whatever the bathymetry and topography and all that. So
one other thing we were discussing, maybe related to this, is anything that is run on the CSM, CSL accounts. Like all of you, you have your data management plan in your proposals to NSF. We also have one for CESM. And so if it's run on Paleo Working Group time, whether by us or someone else, the data and the boundary condition files all need to be released within 1 year of the completion of, and we're talking about production simulations, not some small development, or until the paper is submitted. So there is a deadline for doing that. And like Sophia said, maybe at least for the boundary conditions, contacting the PI on that would make sense, because I can just direct you to them, and maybe they're like, I know Carboniferous, I think you had several different boundary conditions, so you can talk to the researcher about it. I don't know if that, I assume NSF also has policies, but I don't know what they are. I tried to find them. The challenge then is, and I know some people have mentioned it, is like our transient last interglacial, it was put on the Earth system grid, anybody can access it. So there's really no way we can protect from duplicate projects. 2 different grad students at 2 different places could decide to use it for the exact same thing. And it's public after this year, after the year. There's some flexibility because sometimes it takes a while to get everything processed, but that's generally the case. So yeah, if a student, grad student needs, let's say, the Eocene boundary conditions, they could contact Jean, or the Carboniferous ones, contact Sophia, or Pliocene, or whatever it is. So.
Okay, does anyone have any further comments, questions? Okay, we are already late. but not by a lot. So maybe it's time to conclude. Okay,
Thanks
thank
for-
you, everyone.
Thanks for hanging around.
Yeah. Question for Jean, do you want the organizing committee to stay on now or come back at 2? I could do either.
Maybe we can come back later.
Okay.
Thank you.
Thank you. So please.
Thanks everyone for
Thank you.
participating.
Bye.
Thanks.
See you guys
Thank you.
later.
Okay, so we're coming back in like 25 minutes?
No, I
Or
think
wait,
in
An hour and
25.
25. Okay, gotcha.
Just
Okay.
save the chat.
Yeah.
I don't know if Elizabeth saves the chat or not, but
I think she does, but you
Okay.
might save it anyway.